In the quiet hours of the night, when the universe feels close enough to touch, a strange truth begins to unfold. For generations, we believed black holes were the ultimate monsters of the cosmos, but a deeper mystery may be hiding behind their shadow. A paradox born from the collapse of dying stars, a hollow sphere filled not with darkness, but with something far more unsettling. Dark energy trapped inside a shell as thin as a dream. What if the things we call black holes aren't black holes at all? What if the universe has been hiding its real monsters in plain sight? Like and subscribe if you enjoy these cosmic journeys. It helps us keep exploring the unknown together. Settle in, slow your breath, and join me on a quiet voyage into the strangest objects ever imagined. Let's begin. For a century, we believed black holes were the universe's final word, cosmic abysses from which nothing could escape. But beneath that certainty lies a quiet rebellion, a whisper from physics hinting that something even stranger may be hiding in the dark. Black holes have always held a special kind of power over the human imagination. They are the ultimate mystery boxes of the cosmos, regions where gravity becomes so fierce that it bends not only space, but time itself. For decades, we pictured them as cosmic traps, devouring everything that strayed too close. Stars, gas clouds, even entire planets could be swallowed whole. Their stories ended by a boundary from which not even light could return. But sometimes, the universe has a habit of shifting beneath our feet, revealing that what we thought was certain was only the beginning of a deeper puzzle. As astronomers peered closer, through radio telescopes, through gravitational wave detectors, and through the Event Horizon Telescope itself, they found shadows that didn't quite behave the way we expected. Light curved, but perhaps too perfectly. Collisions echoed through space-time, but with faint signatures that seemed out of tune. Even the mathematics of relativity hinted, gently, that something beneath those dark silhouettes might be more complicated than a simple abyss. The idea is subtle, almost unsettling. What if the darkness we see is not a hole at all, but a shell? What if the interior is not infinite density, but something else entirely? It is here that physics begins to shift from the familiar to the dreamlike. Some researchers propose that when a star collapses, it may not form a singularity at all. Instead, the collapse could pause at the brink, forming something hollow, smooth, and strangely stable. A structure with no edge, no bottom, no infinite compression. Only a boundary so thin and tense that the entire star's mass becomes a kind of cosmic membrane. From a distance, to the untrained eye, or even to our most advanced telescopes, that shell would appear indistinguishable from a black hole. It would cast the same shadow. It would warp space-time in almost the same way. It would mimic the silence and the darkness perfectly, hiding its true nature behind a flawless disguise. And yet, it wouldn't be a black hole at all. This possibility softens the universe in a strange way, replacing the cold finality of singularities with something gentler, something more orderly. A gravastar, if such things exist, would be a quiet rebellion against the collapse of matter, a cosmic compromise between gravity and quantum physics. And this is where the mystery deepens. The more we study black holes, the more they seem to behave like something else, something hollow, something that returns faint echoes after collisions, something with a surface, or at least the suggestion of one. The universe, it seems, may not be done surprising us, and the shadow we thought we understood might not be what it appears to be at all. Unlike black holes, gravastars have no singularity, no tear in the fabric of reality, only a surface so strange it behaves like the edge of existence itself, absorbing everything without ever letting anything fall in. Imagine approaching such an object, not a cosmic pit, not a bottomless well of gravity, but a sphere with a surface so peculiar that physics itself must pause and reconsider. There is no down beyond it, no plunge into a void. Instead, you meet a boundary, thin, taut, shimmering in ways our eyes could never see. where the collapse of a massive star has halted at the last possible heartbeat. It does not swallow matter the way a black hole does. It does not tear apart the atoms of anything that strays too close. Instead, matter brushes the shell and disappears into it, as if pressed into a barrier that accepts everything yet allows nothing to fall through. A gravastar doesn't gulp. It doesn't devour. It absorbs. But that absorption is not consumption, it's transformation. Matter that reaches the shell doesn't fall inward. It spreads across the boundary like ink on paper, adding to the tension of the structure, reinforcing it. The object grows not by pulling things into an abyss, but by wrapping them around itself, layer by layer, like the universe's strangest cocoon. To an outside observer, this surface behaves almost exactly like an event horizon. Light curves around it, vanishing into its grip. Time slows near its edge. Shadows deepen, silence thickens. The shell is so perfectly dark it becomes a nearly flawless impersonator of a black hole. But beneath the disguise lies profound difference. A black hole is defined by its emptiness, its singularity. A gravastar is defined by its fullness, its internal pressure. Inside is not chaos, but order. Not collapse, but a quiet equilibrium held by vacuum energy so strong it can resist the entire weight of a dying star. Picture it, a hollow sphere inflated from within by something that pushes outward with relentless calm. A monster, yes, but a silent one. A creature without a mouth, feeding not by hunger but by inevitability. Anything that touches it becomes part of it, and this creates an illusion so complete, so convincing, that to our telescopes the difference disappears. We see the same shadow, the same darkness, the same gravitational pull. But what lies beneath that shadow is not a gateway to oblivion. If gravastars exist, they would linger longer than black holes, stable and eternal. They would not evaporate over aeons. They would not leak information into Hawking radiation. They would simply remain, smooth, seamless, cosmic statues carved by the collapse of stars. A monster, yes, but a monster of a different kind. Not a devourer, but a boundary. Not a mouth, but a wall. And as we peer deeper into the cosmos, we begin to realize that what we once believed to be cosmic jaws may instead be something far more enigmatic, something that absorbs reality, not by swallowing it, but by gently folding it into itself, forever part of the shell. Unlike black holes, gravastars have no singularity, no tear in the fabric of reality, only a surface so strange it behaves like the edge of existence itself, absorbing everything without ever letting anything fall in. Imagine approaching such an object, not a cosmic pit, not a bottomless well of gravity, but a sphere with a surface so peculiar that physics itself must pause and reconsider. There is no down beyond it, no plunge into a void. Instead, you meet a boundary, thin, taut, shimmering in ways our eyes could never see, where the collapse of a massive star has halted at the last possible heartbeat. It does not swallow matter the way a black hole does. It does not tear apart the atoms of anything that strays too close. Instead, matter brushes the shell and disappears into it, as if pressed into a barrier that accepts everything yet allows nothing to fall through. A gravastar doesn't gulp. It doesn't devour. It absorbs. But that absorption is not consumption, it's transformation. Matter that reaches the shell doesn't fall inward. It spreads across the boundary like ink on paper, adding to the tension of the structure, reinforcing it. The object grows not by pulling things into an abyss, but by wrapping them around itself, layer by layer, like the universe's strangest cocoon. To an outside observer, this surface behaves almost exactly like an event horizon. Light curves around it, vanishing into its grip. Time slows near its edge. Shadows deepen, silence thickens. The shell is so perfectly dark it becomes a nearly flawless impersonator of a black hole. But beneath the disguise lies profound difference. A black hole is defined by its emptiness, its singularity. A gravastar is defined by its fullness, its internal pressure, Inside is not chaos, but order, not collapse, but a quiet equilibrium held by vacuum energy so strong it can resist the entire weight of a dying star. Picture it, a hollow sphere inflated from within by something that pushes outward with relentless calm. A monster, yes, but a silent one. A creature without a mouth, feeding not by hunger but by inevitability. Anything that touches it becomes part of it, and this creates an illusion so complete, so convincing, that to our telescopes the difference disappears. We see the same shadow, the same darkness, the same gravitational pull. But what lies beneath that shadow is not a gateway to oblivion. If gravastars exist, they would linger longer than black holes, stable and eternal. They would not evaporate over aeons. They would not leak information into Hawking radiation. They would simply remain, smooth, seamless, cosmic statues carved by the collapse of stars. A monster, yes, but a monster of a different kind. Not a devourer, but a boundary. Not a mouth, but a wall. And as we peer deeper into the cosmos, we begin to realize that what we once believed to be cosmic jaws may instead be something far more enigmatic, something that absorbs reality, not by swallowing it, but by gently folding it into itself, forever part of the shell. Where a black hole bends space-time with brute force, a gravastar shapes it like a gentle sphere of pressure and emptiness, an object more elegant, more alien, and far more unsettling. To understand the difference, imagine space-time as a vast, invisible fabric stretching through everything. A black hole punches into it like a fist through canvas, creating a steep, violent gorge that pulls everything toward its center. A gravastar, however, is more like a perfectly inflated bubble resting on that same fabric, smooth, delicate, but radiating an invisible pressure that pushes outward, subtly reshaping the world around it. It is the difference between collapse and resistance, between gravity unleashed and gravity transformed. The warping around a gravastar is not the scream of space-time stretching toward a singularity. It is a whisper, soft, controlled, almost graceful. This is what makes gravastars so disquieting. They warp the universe without ever breaking it. They imitate the gravitational field of a black hole with astonishing precision. Yet their influence is born not from infinite density, but from the tension of the shell and the swelling push of dark energy within. Approach one, and you would feel the familiar pull of gravity, the same steady descent you would expect near a black hole. Light would curve around it, tracing elegant arcs. Time would slow, moments stretching thin as the object's presence deepened its grip on your perception. And yet, beneath that familiar behavior is a geometry that quietly betrays the truth. The space-time around a gravastar is almost too smooth. Near a black hole, the curvature grows infinitely steep, like a cliff dropping into darkness. Near a gravastar, the descent slows before reaching that extreme because there is no true abyss beneath the surface. Instead, gravity curves inward and then settles, stabilizing against the outward push from the interior. It is a balance achieved not by collapse, but by an extraordinary equilibrium. This equilibrium creates a strange calm, a calm that feels unnatural. The exterior space-time appears obedient, predictable, almost serene. But beneath that calm exterior lies incredible tension, a boundary holding back an ocean of exotic energy, a tension that exerts its influence silently, without the catastrophic distortions associated with singularities. And this creates an illusion, the illusion of a black hole's gravity, without the black hole's violence. From a distance, you could not tell the difference. The gravitational lensing would match. The shadow would be indistinguishable. Even the tug on nearby stars would appear identical. But the space-time beneath that disguise is not spiraling endlessly inward. It is bending smoothly, wrapping itself around a hollow core. A gravastar warps space not by collapsing it, but by holding it outward, like a bubble resisting compression. It is elegant, it is quiet, and it is deeply alien. It suggests that gravity, This force we think of as relentless and unforgiving may have secret modes of behavior, secret compromises, and secret shapes it can settle into when pushed to its limits. Perhaps not everything in the universe collapses into violence. Perhaps some things collapse into silence. Inside a gravastar, space isn't filled with matter, but with something deeper, a sea of dark energy, swirling in perfect equilibrium, pushing outward against the weight of collapsing stars. To imagine such a place, you must set aside everything you know about interiors. We are used to worlds that contain things: rock, gas, fluid, fire. Even the cores of planets and stars have familiar textures, pressures, temperatures. A gravastar's interior is nothing like this. It is not a chamber stuffed with particles, nor a furnace of nuclear fusion. It is a vast, silent void held open by a force that behaves more like a thought than a substance. Dark energy. A concept already mysterious in the wider universe, becomes even stranger inside a gravastar. Here, it is not scattered thinly across galaxies. It is condensed, gathered, concentrated into a single sphere of pressure. It is the breath that expands the bubble, the unseen hand that resists gravity's attempt to crush the star into oblivion. This interior pressure is not violent. It is not explosive. It is calm, constant, the most balanced force in nature. In ordinary space, dark energy pushes galaxies apart. But inside a gravastar, that same repulsive force pushes against the inward pull of a collapsing star, matching it perfectly. One force wants to shrink everything to a point. The other wants to expand everything infinitely. The result is neither collapse nor explosion, but equilibrium. A suspension, a pause, a stillness so complete it defies intuition. If you could drift inside, you would see no stars, no dust, no particles drifting lazily through the void. Instead, you would find an emptiness that feels full of tension, full of potential, full of an invisible pressure that presses equally in all directions. Space itself is doing the pushing, and this is what makes a gravastar truly alien. Its interior is not a place. It is a force. A region where the fabric of space-time is inflated, like a perfectly spherical lung held at a steady breath. No motion, no turbulence, no sound, only the silent insistence of dark energy refusing to let gravity finish its work. The shell of the gravastar becomes the boundary between two competing realities: the inward collapse of ordinary matter and the outward expansion of vacuum energy. The result is a cosmic stalemate, frozen in time. And yet this balance is not fragile. Paradoxically, it may be one of the most stable configurations in the universe, because inside, nothing changes. Nothing cools or heats. Nothing falls or rises. Nothing drifts or collapses. Time has no work to do in a place without events. This calm interior might last longer than the lifetime of galaxies. While black holes slowly evaporate through Hawking radiation, a gravastar might remain intact indefinitely, its vacuum heart unchanged for trillions upon trillions of years. A vacuum, yes, but a vacuum with purpose. A vacuum that pushes, expands, resists. A vacuum that holds back the death of a star. Inside a gravastar, emptiness becomes structure, and nothingness becomes the most powerful something in the cosmos. Some stars may reach the brink of forming a black hole, only to stop at the last possible moment, suspended in a state that defies everything we know about gravity. To understand this strange hesitation, imagine the final breaths of a massive star. Its core collapses under its own weight, atoms crush so tightly that electrons fuse with protons, forming a dense sphere of neutrons. For neutron stars, this is where the collapse stops. But for even more massive stars, the crushing continues, deeper and deeper, until gravity becomes irresistible. At this point, the end seems inevitable: the birth of a black hole, the formation of a singularity, the beginning of an event horizon. And yet, there might be another ending. Some theories suggest that just before that final plunge, Before gravity's victory becomes absolute, a different force awakens. Vacuum energy, normally gentle and diffuse, begins to concentrate. It grows stronger as the star shrinks, swelling like a silent tide. And in that last razor-thin moment, as the star teeters on the edge of forming a horizon, this vacuum pressure pushes back. Not violently, not explosively, but decisively. The collapse doesn't continue. The star doesn't vanish. Time doesn't tear. Instead, everything pauses. The matter that was collapsing inward meets an equal outward pressure, creating a perfect balance between implosion and expansion. The star, caught between two incompatible destinies, settles into an entirely new one. It becomes neither a neutron star nor a black hole, but something stranger, something caught in cosmic limbo. This moment is like a breath held forever. A gravastar forms not from collapse, but from collapse interrupted. It is a story of gravity, nearly winning, nearly crushing matter into infinity, but losing at the last possible instant to a force woven into the very fabric of space itself. To an outside observer, this transformation is invisible. Light fades just as it would around a black hole. The star's silhouette darkens. Time slows near its surface. But unlike a black hole, the star's interior never forms a singularity. There is no point of infinite density, no bottomless gravitational well, no final, catastrophic collapse. Instead, the core dissolves into dark energy. The star's life ends not as a corpse, but as a bubble, hollow, stable, held open by the very component that drives the expansion of the universe. This possibility rewrites our understanding of stellar death. It suggests that some stars refuse to accept the fate gravity demands. They step back from the edge, finding equilibrium in the most unexpected of places. A gravastar is a star that almost died the ordinary way, but then chose an extraordinary one. It becomes a monument to balance, a monument to forces we barely understand, a structure held together not by atoms or heat, but by the push and pull of space-time itself. The universe, in these quiet corners, seems to remind us that endings are not always endings. Sometimes, collapse becomes transformation. Sometimes, destruction becomes creation. And sometimes, even a dying star refuses to fall into darkness. A gravastar's surface is no thicker than a human hair stretched around a city, yet its tension is so immense it could hold back an entire collapsing star. It is one of the strangest concepts in astrophysics. The idea that everything which defines a gravastar, its mass, its structure, its gravitational influence, could be concentrated into a boundary so impossibly thin that it approaches pure geometry. This shell is not like the crust of a planet or the surface of a star. It is not made of ordinary atoms arranged in familiar patterns. Instead, it is composed of exotic matter, a state so unusual that it barely resembles the particles we know. Imagine a membrane stretched with infinite patience, smooth and seamless, wrapping itself around a hollow sphere of dark energy. This boundary is where the collapse of the star finally halts, where matter becomes something other than matter, where the laws of physics shift from familiar equations into the realm of the theoretical. Despite its thinness, the shell carries the weight of an entire star. Its tension is immense, not the tension of stretching rubber or bending metal, but the tension of space-time itself resisting collapse. This membrane, if it exists, would be among the strongest structures in the universe. It must be. Every second, gravity tries to crush it inward. Every second, the dark energy core pushes outward. The shell stands between these two cosmic giants, never yielding to either. The result is a perfect balance, maintained across a surface so delicate it would make a soap bubble seem colossal by comparison. If you could somehow approach it, slowly, carefully, you would never truly touch it. The gravitational time dilation would stretch your movements. The light around you would warp, curling back in elegant arcs. Your perception of time would shift, minutes stretching into hours as you neared the boundary. And the shell, though unimaginably thin, would feel infinite, as if every point on it were connected to every other point. It is a surface that behaves like an event horizon without being one. Anything that reaches it becomes part of it, not by falling inward, but by being absorbed into the membrane. Matter spreads across the shell, adding mass, increasing tension, reinforcing the structure. Nothing penetrates deeper, nothing crosses into the central void. The shell is the gatekeeper, the guardian of the dark energy heart. Some describe it as a horizon you can touch, though touching it would be unlike touching anything else in existence. It has no texture, no temperature, no physical sensation as we know it. It is a mathematical boundary manifested as physical reality, a place where gravity stops, where collapse ends, where the universe holds its breath. It is a surface thin enough to be considered nothing, and strong enough to hold back everything. A Gravastar's shell challenges our intuition, reminding us that the universe does not always build with bricks of matter. Sometimes it builds with tension, with energy, with the delicate balance of forces we barely understand. A surface as thin as thought, a boundary that keeps a star from vanishing, a membrane stretched across the edge of possibility. At the center lies not matter, nor light, nor heat, but vacuum energy, an exotic substance that feels less like physics and more like the blueprint of reality. To picture such a core, you must let go of the instinct to imagine something tangible, a glowing furnace, a swirling vortex, a sphere of gas. The heart of a Gravastar is nothing like the interiors of stars or planets, or even the emptiness of normal space. It is a vacuum, yes, but not the kind we understand. This vacuum is dense with potential, saturated with the energy that shapes the universe on its largest scales. It is the same mysterious force believed to push galaxies apart, now gathered into a single, concentrated region. Inside this sphere, nothing moves, nothing collides. Instead, space itself hums with a quiet pressure, as if the laws of the cosmos are rehearsing their lines in perfect silence. It is a place where emptiness becomes substantial, where the absence of matter is replaced by the presence of pure energy. This dark energy heart does not shine, does not vibrate, does not create heat. It simply exists, pushing outward with steady determination. It is the quietest force imaginable, yet strong enough to counteract the crushing weight of a dying star. If you could somehow drift into that core, ignoring, for a moment, the impossibility of crossing the shell, you would find yourself in a realm without familiar landmarks. There would be no particles to reflect light, no atoms to scatter sound. You would float in a space that feels infinite, yet enclosed, empty, yet full, silent, yet powerful. Here, gravity and expansion coexist in a delicate stalemate. The inward pull of the star that once was, the outward push of the vacuum that now is. Two cosmic intentions, perfectly balanced. Some theorists describe this region as a false vacuum, a state where space exists in its most potent form, pregnant with possibility, yet frozen in stillness. Others imagine it as a bubble of the early universe, preserved like a fossil, a pocket of primordial energy untouched since the moment of the Big Bang. Both descriptions capture the same idea. The Gravastar's core is not just empty, it is foundational. It resembles the raw scaffolding from which reality is built, the unseen structure underlying all space and time. The laws that govern the movement of galaxies and the birth of stars seem to echo faintly within this void, as if the Gravastar contains a small, silent memory of creation itself. This makes the core feel paradoxical. It is nothing. There is no matter. And yet it is everything. There is only energy. It is a region defined not by what exists within it, but by the force it exerts on everything around it. Without emitting a single photon, without creating a single spark, the core holds the entire Gravastar open, resisting collapse with cosmic serenity. In a universe filled with blazing stars, whirling galaxies, and violent explosions, the Gravastar's core is a reminder that some of the most powerful things are quiet. Some of the most extraordinary things are empty. And sometimes, nothingness can contain the deepest mysteries of all. Photons caught near a Gravastar do not fall inward. They orbit endlessly, trapped on a razor-thin ring of light that glows invisibly across the cosmos. This delicate structure is known as the photon sphere, a region of space where light itself becomes a captive. In the familiar picture of a black hole, this sphere marks the last desperate loop light can take before succumbing to the event horizon. But around a gravastar, the story changes. There is no horizon waiting beneath, no infinite descent, no singularity pulling light into the unknown. Instead, the photons skim the shell, circling it like fireflies orbiting a lantern made of gravity. They are not swallowed. They are not reflected. They are simply bound, caught in a perfect dance along the curvature of space-time. If you could stand at a distance and look at this place, not with human eyes, but with senses expanded to cosmic scales, you would see the faintest suggestion of a halo, not glowing, not shimmering, but bending space just enough to leave the imprint of its presence. A ring of trapped light, circling endlessly, forming a boundary where reality curves back upon itself. The light never reaches the interior. It never dives deeper. It never escapes outward. It is suspended in a kind of gravitational limbo, forever falling around the gravastar, never closer, never farther, like a thought repeating itself across eternity. This orbit is razor-thin, balanced with exquisite precision. A photon, passing a fraction of a millimeter too wide, escapes into the void. A fraction too close, and it smears across the shell, absorbed instantly into the gravastar's mass. Only those that hit the exact right path trace that circular prison. And so this sphere becomes a quiet record of every photon that has ever ventured too close, a ghostly catalogue of starlight from across the galaxy. Light from ancient suns, light from wandering nebulae, light from distant supernovae. All gathered, all trapped, all circling in silence. To the universe, it is invisible. To physics, it is unavoidable. To a gravastar, it is a necklace made of time. This ring gives the gravastar its deceptive appearance. When telescopes image the silhouette of a black hole, what they truly see is this glowing boundary. The dark center, what we assume to be the event horizon, may not be a hole at all, but the perfectly smooth surface of a gravastar hiding beneath that orbiting light. Even if the object is hollow, even if its interior is a vast bubble of vacuum energy, the photon sphere makes it look identical to a black hole from afar. Light curves sharply, shadows deepen. Space warps into the familiar dark ring we have come to associate with cosmic collapse. But here, the shadow is an illusion. Light is not plunging into a doom-filled abyss. It is circling endlessly around a hollow core. The difference is subtle, almost invisible, yet profound. One is the signature of destruction, the other is the signature of balance. And in the thin, delicate path that photons trace around a gravastar, the universe reveals that even light, its purest traveler, can be caught and held forever by a surface that is not an edge, but a boundary between two very different realities. From afar, a gravastar looks almost identical to a black hole, a perfect cosmic impersonator, but its behavior carries subtle signatures that betray the truth. Unlike a black hole, which swallows everything, including light, into a singularity of infinite density, a gravastar hides a core of repulsive vacuum energy behind a razor-thin shell. To an observer, the outer shell bends and warps light almost as violently as a black hole. Yet the space inside is not a pit of destruction, but a region of extreme yet stable energy. This distinction is subtle, and detecting it requires precision the likes of which humanity has only recently begun to achieve. The light that grazes a gravastar's shell does not vanish entirely. It loops, twists, and sometimes escapes, producing faint echoes in the cosmic microwave background or tiny flickers in the radiation from nearby stars. These whispers of light are like a signature tune, unique to gravastars, faint but discernible if one knows where and how. Gravastars challenge our assumptions about gravity, matter, and the limits of physics. They are neither purely theoretical nor fully confirmed, yet their existence would elegantly resolve some paradoxes that have long plagued black hole physics. Chief among these is the information paradox. Black holes, according to classical theory, erase the history of everything they consume. Gravastars, with their non-singular cores, might preserve information in subtle ways, encoded within the quantum fluctuations of their vacuum energy, allowing the universe's bookkeeping to remain intact. The shell itself is a marvel of cosmic engineering, or rather, cosmic happenstance. It is extraordinarily thin, perhaps only a few millimeters across for a gravastar with the mass of the Sun, yet it withstands the pull of gravity that would crush ordinary matter into oblivion. Its composition is exotic, a fluid-like layer of ultra-dense matter, balanced perfectly against the outward push of the vacuum energy it encloses. This balance creates a state of almost miraculous stability, a structure that can last longer than the age of the universe itself. Nearby, space behaves strangely. Objects approaching a gravastar experience tidal forces that mimic those near a black hole, but they do not encounter an event horizon. Infalling matter may circle, oscillate, or be flung back outward. The phenomenon has led theorists to describe gravastars as time mirrors, where the flow of events around them bends so dramatically that cause and effect are distorted, but never entirely erased. For astronomers and astrophysicists, this is a tantalizing frontier. Observing a gravastar could offer a window not just into exotic matter, but into the fundamental interplay between space, time, and information. Gravastars remain elusive, shimmering at the edge of detectability like a desert mirage. Yet every telescope and every observatory that pushes the boundaries of sensitivity brings us closer to distinguishing these cosmic phantoms from their more notorious cousins. The quest is as much about understanding the universe as it is about confronting the limits of our imagination, a reminder that the cosmos may hold structures more subtle, more intricate, and more astonishing than we have yet dared to dream. Some physicists believe that gravitational waves might echo, tiny reverberations in space-time that hint at a hollow interior rather than a bottomless pit. Unlike the smooth fade of waves absorbed by a black hole, a gravastar's shell could reflect minute ripples back into the cosmos. These echoes are subtle, delayed whispers following the initial gravitational wave, faint signatures that, if detected, could reveal the presence of a structure where nothing was thought to exist. Gravitational waves, ripples in the very fabric of space-time, are already a revelation. They are the sound of the universe in motion, colliding neutron stars, merging black holes, the tremors of cosmic cataclysms billions of light-years away. To imagine that these waves could bounce off an object instead of disappearing into a singularity transforms our understanding of the cosmos. A gravastar, with its dense but non-singular shell, might act like a cosmic drumhead, vibrating in response to passing gravitational waves and sending a faint aftershock outward, a ghostly echo of events long past. These echoes, if observed, would be a message written in the language of space-time itself. They carry information about the gravastar's size, its shell composition, and even the properties of the exotic vacuum energy within. In principle, astronomers could distinguish a gravastar from a black hole not by what it swallows, but by what it whispers. Each echo encodes a cosmic fingerprint, a subtle deviation from the pattern predicted for a traditional black hole merger. Detecting them requires unprecedented sensitivity. Instruments capable of perceiving tremors billions of times weaker than the most delicate vibrations on Earth. The implications are profound. For decades, black holes have been regarded as ultimate erasers. Once matter and energy cross the event horizon, their information is lost to the universe. Gravastars suggest a different story, one in which the universe retains a trace of everything it encounters. Echoes in space-time could carry these traces outward, offering physicists a way to read the history of objects that have interacted with the gravastar's shell. It is a hint that nature may preserve information even in its most extreme environments, a resolution to puzzles that have long vexed theoretical physics. Observing such echoes is no simple task. They arrive as tiny, delayed signals, often buried in the noise of gravitational wave detectors. Yet each potential detection is a window into the impossible, a chance to glimpse a hollow core masquerading as a singularity, a structure defying conventional expectations of gravity. Even a single confirmed echo would reshape our understanding of space-time, of extreme matter, and of the cosmic boundaries between presence and absence. In this sense, gravastars are not just astrophysical curiosities. They are challenges to our intuition. They remind us that the universe is subtler than our models, that even in the darkest, most extreme corners of space, surprises await. The echoes from these objects are more than mere signals. They are invitations to question, to explore, and to imagine what might exist at the edge of reality, where the universe itself seems to murmur its secrets to those who listen carefully enough. A collapsing star may appear to vanish behind a horizon, but in the Gravastar model, the horizon never truly forms, only the illusion of one. From a distance, the dying star behaves almost exactly like a black hole, shrinking rapidly, curving space so sharply that light struggles to escape. To an observer watching from afar, it seems as though the star has disappeared forever, swallowed by a bottomless void. Yet, in reality, nothing has crossed an event horizon, because a gravastar's exotic interior halts the collapse before a true singularity can form. This subtle difference transforms the story of stellar death. In the traditional black hole scenario, matter plunges into oblivion, compressed into infinite density, leaving behind an enigmatic singularity. A gravastar, however, replaces that singularity with a region of vacuum energy, a hollow heart sustained by pressure that defies gravity itself. The outer shell, ultra-thin, incredibly dense, shields this inner core and bends space so sharply that the star's disappearance is convincingly complete. It is a cosmic sleight of hand. The universe believes it sees an ending, but the core persists, a lingering heartbeat beneath the illusion of finality. For physicists, this illusion raises tantalizing possibilities. Because the horizon never truly forms, the laws of quantum mechanics remain unbroken. Information about the star's collapse, its composition, even the path of particles it has consumed, may be preserved in subtle ways. Gravitational waves, neutrino fluxes, and radiation reflected or emitted from the shell all carry traces of the star's story. In principle, these signals offer astronomers a chance to distinguish a gravastar from a black hole, not by what it hides, but by how it whispers, by how it bends the flow of energy and information around it. The dynamics of the collapsing star are equally mesmerizing. As the star contracts, its core pushes back against gravity, balancing extreme forces in a delicate equilibrium. The shell forms almost instantaneously in cosmic terms, an invisible barrier that ensures the interior does not collapse into a singularity. Observers far away witness the star dimming, its light stretched and reddened, its final flashes fading as if swallowed by a horizon. But this is a trick of perspective, a cosmic masquerade. The star hasn't died, it has merely changed form, adopting a guise designed to fool even the most vigilant eyes. This performance is more than a theoretical curiosity. It challenges the way we define death on a cosmic scale. If stars can pretend to die, then the universe itself is less absolute, more mysterious than previously imagined. Gravastars suggest that endings may be illusions, and beginnings may hide beneath layers we cannot yet penetrate. In watching a star collapse, astronomers are not merely witnessing the death of matter. They may be glimpsing the universe's capacity for subtlety, its ability to hide truths in plain sight, and its persistent refusal to yield its deepest secrets too easily. At its core, the Gravastar model reframes our understanding of collapse and disappearance. The star does not vanish, it transforms, and the horizon is only a shadow on space-time. For those who study the cosmos closely, this is a profound revelation. In the universe's darkest corners, nothing is ever truly lost, and the act of disappearing may be, paradoxically, an eternal presence in disguise. The outer boundary is thought to be made of ultra-dense matter so compressed that atoms lose their identity, becoming pure structure. Imagine matter stripped of all familiar properties, no electrons orbiting nuclei, no chemical bonds, no temperature in the way we understand it, leaving only a lattice of unimaginable density. This shell, though incredibly thin compared to the scale of the Gravastar itself, is strong enough to resist the colossal inward pull of gravity that would crush ordinary matter without hesitation. It is a razor's edge between existence and oblivion, a boundary that defines the object yet contains nothing conventional inside. The shell's strength is more than mechanical, it is cosmic. Every particle within it is bound by forces that transcend normal physics, organized in a state that theoretical models describe as exotic. Some physicists liken it to a fluid frozen by space-time itself, a tension so precise that the shell can maintain stability even as a gravastar grows to several times the mass of our Sun. This is why the gravastar can exist for billions of years without collapsing or dissipating, a perfect equilibrium of pressure, density, and gravity. Light interacts with the shell in extraordinary ways. Photons that graze its surface can be bent into orbits that circle the object multiple times before escaping, or they can become trapped temporarily, creating glowing rings of light that shimmer briefly in space. For distant observers, this bending is almost indistinguishable from the effect of a black hole, which is why gravastars have remained so elusive. Yet careful measurements of these subtle distortions could reveal the shell's presence, its finite thickness, and the properties of the matter it contains. The shell is also a mediator between the gravastar's interior and the outside universe. Beneath it lies the vacuum energy that forms the core, a region of repulsive pressure that pushes outward, counterbalancing the relentless pull of gravity. The shell transmits this force with perfect fidelity, maintaining the object's integrity while preventing collapse. It is a structure where geometry and matter become inseparable, a surface that is simultaneously barrier, bridge, and boundary. Despite its infinitesimal thickness, the shell defines the gravastar's identity. Without it, the vacuum energy within would expand uncontrollably. With it, the gravastar masquerades flawlessly as a black hole. Its mere existence raises profound questions. How can matter organize itself into a state that defies all conventional limits? How does the universe allow such perfect balance to emerge from chaos? These are not just technical puzzles, they are invitations to reconsider what matter, pressure, and stability truly mean on a cosmic scale. The shell also hints at something more philosophical. The universe can create boundaries that are finite yet infinite in strength, delicate yet unyielding. It is a reminder that even the thinnest structures can carry the weight of entire stars, and that extremes of physics do not always follow the intuitions we develop on Earth. In a gravastar, the edge is everything. The thin, impossibly strong shell that preserves the interior, sustains the illusion of collapse, and whispers a truth about the universe that challenges every expectation we hold about matter, energy, and the limits of what can exist. Black holes and gravastars cast identical shadows, making them indistinguishable, unless you know exactly where to look. From a distance, both objects warp space and bend light with such intensity that they appear as dark voids outlined by a glowing ring of radiation. To the untrained eye, or even to powerful telescopes, the difference is imperceptible. It is a cosmic sleight of hand, a masquerade so convincing that centuries of observation might mistake one for the other. Yet beneath this perfect mimicry, subtle discrepancies ripple through the light and gravitational waves they influence, whispers that betray the true nature of the imposter. The shadow itself is an illusion, shaped by the extreme curvature of space-time around the object. In the case of a black hole, the shadow marks the edge of an event horizon, a boundary beyond which nothing can return. For a gravastar, the shell halts collapse just shy of forming a horizon, creating a nearly identical silhouette. Photons skim the surface, circling the shell multiple times before escaping, forming a luminous halo that deceives even the most precise instruments. It is an identity so convincing that only the most delicate measurements, the tiniest deviations in light paths or gravitational echoes, can reveal the truth. Physicists search for these discrepancies with extraordinary care. Gravitational waves, traveling through space-time, can interact differently with a hollow gravastar than with a singularity. Minute echoes, tiny delays, or variations in amplitude may indicate that the object has an interior structure rather than a point of infinite density. Similarly, high-resolution imaging of the photon ring, the light trapped in orbit near the surface, can reveal subtle oscillations, a flicker here or a shift there, betraying the presence of a shell instead of a singularity. It is a cosmic game of spot the difference, played on scales so vast and energies so extreme that humanity is only now developing the tools to participate. This perfect mimicry is not accidental. Gravastars exist at the edge of physical law. Their design, or rather, their natural formation, optimized by the same forces that govern black holes. Gravity, pressure, and vacuum energy conspire to create an object that is stable, long-lived, and visually indistinguishable from the most extreme known bodies in the universe. The very fact that they can exist without collapsing into singularities, while still casting shadows identical to black holes, is a reminder that nature often operates in ways more subtle and more intricate than our simplest models suggest. Yet the universe allows clues to seep through. The most patient observers, watching over years and decades, may notice the faintest hints: light trapped temporarily inside the shell, gravitational waves that linger just a fraction longer than expected, or the tiniest deviations in orbital paths of nearby stars. These are the telltale signs that the universe's perfect imposter has been caught in the act, revealing a complexity hidden beneath the shadow. In this way, gravastars remind us that appearances can be deceiving, even on a cosmic scale. The universe is capable of constructing illusions so convincing that entire generations of astronomers can be fooled, yet it leaves breadcrumbs for those willing to look carefully. In the dance of light and gravity, the shadow of a gravastar is not just a silhouette, it is a challenge, a puzzle, and an invitation to peer deeper into the truth behind the cosmos's most enigmatic facades. A gravastar's interior geometry is inverted. Space pushes outward instead of pulling inward, turning gravity on its head. Inside the hollow core, the vacuum energy exerts a repulsive pressure so extreme that it counteracts the immense pull of the star's outer shell. Where we expect gravity to crush matter inward, here, space itself resists compression, expanding against the collapse. It is a paradox that defies intuition. The very fabric of space-time is working in reverse, holding the gravastar together and preventing the formation of a singularity. This inverted geometry creates a reality unlike anything experienced elsewhere in the universe. Light, matter, and energy inside the gravastar do not follow the same paths dictated by ordinary gravitational fields. A photon approaching the center may be bent outward instead of inward, trapped in a subtle orbit along the shell, or even ejected back into space after grazing the interior. Particles behave unpredictably, oscillating in patterns dictated not by attraction but by this extraordinary repulsion. To enter a gravastar is to step into a world where the rules of gravity are flipped, where the center pushes instead of pulls, and the interior is less a pit and more a bubble of sustained tension. The mathematics describing this geometry are as elegant as they are unsettling. Equations that govern black holes, the Schwarzschild and Kerr metrics, cannot fully capture the behavior of a gravastar. Instead, theorists use modified models of spacetime, where the metric coefficients change sign in the interior, reflecting a repulsive core. In essence, the gravastar's interior is a region of space-time with negative curvature, a place where the usual intuitions about collapse, density, and singularity break down entirely. This inversion also influences the object's exterior. The shell must perfectly balance the outward pressure of the interior against the relentless pull of gravity. Even a tiny imbalance would destroy the structure, collapsing it into a black hole or dispersing it entirely. The result is a cosmic equilibrium so delicate that it seems almost engineered, yet it emerges naturally from the laws of physics when matter reaches extreme density under collapse. The gravastar is a manifestation of geometry itself, a star whose interior forces space to behave in ways that challenge both imagination and calculation. For astronomers, this inverted geometry holds promise for discovery. Light and gravitational waves interacting with the shell can carry subtle imprints of the unusual interior. Tiny deviations in orbital dynamics near the Gravastar, or faint echoes in space-time, are hints that gravity inside is not what it seems. Observing these effects could provide direct evidence of a region of space where the conventional rules of attraction have been turned inside out, offering a glimpse of phenomena that feel almost science-fictional but are grounded in theoretical physics. Ultimately, the Gravastar's inverted geometry is a reminder that the universe does not owe us intuition. It is a realm where space itself can resist, push, and defy, where matter is constrained not by collapse but by expansion from within. To witness a Gravastar is to confront the possibility that even the most fundamental forces, gravity, pressure, and curvature, can combine to create something entirely unexpected, a structure that challenges everything we thought we knew about the shape and behavior of the cosmos. There is no infinite density, no breakdown of mathematics, only a stable, smooth boundary where physics remains whole. Unlike a black hole, where equations collapse under the weight of a singularity, a Gravastar preserves the integrity of space-time. Its core is not a point of infinite compression but a region filled with vacuum energy that exerts repulsive pressure, balancing the gravitational pull of the outer shell. In this way, the universe avoids the paradoxes of classical collapse, maintaining continuity and allowing the laws of physics to remain unbroken, even in the most extreme conditions. The absence of a singularity transforms the very notion of gravity. In a Gravastar, space-time curves intensely, bending light, warping trajectories, and distorting the flow of time, but it never tears. Matter can approach the shell, even circle it in prolonged orbits, without ever encountering a point where physics fails. No infinities emerge, no equations diverge, and no information is lost irretrievably. The Gravastar is a cosmic middle ground, a structure extreme enough to mimic a black hole in appearance and gravitational influence, yet mathematically consistent and physically complete. This stability extends across cosmic scales. While black holes are defined by horizons beyond which nothing can return, a Gravastar's boundary is a smooth transition between interior and exterior. The ultra-dense shell halts collapse with precision, while the repulsive core pushes outward, creating a perfect equilibrium. From the perspective of a distant observer, the Gravastar behaves almost identically to a black hole. The bending of light, the gravitational lensing, the tug on nearby stars all match predictions, but the interior tells a different story, one in which collapse does not end in catastrophe, but in balance. The implications for physics are profound. Singularities have long represented a breakdown in our understanding of gravity and quantum mechanics, signaling points where the known laws of nature cease to apply. Gravastars offer a resolution, extreme gravity without paradox. They are laboratories of possibility, where space-time can be warped to near absolute limits without collapsing into mathematical nonsense. Observing a Gravastar would confirm that the universe can create structures so extreme that they challenge intuition yet remain internally coherent and physically meaningful. Even the behavior of light and gravitational waves reinforces this idea. Photons skimming the shell may loop multiple times, and gravitational waves can reflect subtly from the boundary, producing echoes that carry information about the interior. Unlike a black hole, which erases these details behind an event horizon, a Gravastar preserves them. Every ripple, every flicker, every tiny deviation in motion becomes a potential window into the core of the object, a confirmation that gravity here is immense but finite, extreme but never infinite. Ultimately, a Gravastar demonstrates that nature's extremes need not be paradoxical. Gravity can reach heights that would destroy ordinary matter, yet the universe provides mechanisms, exotic matter, vacuum energy, ultra-dense shells, that preserve coherence. In this way, the Gravastar is a triumph of cosmic subtlety, a place where the universe stretches the rules without breaking them, where singularities vanish, and where physics, at its most extreme, remains whole, elegant, and unbroken. Inside, dark energy pulses like a still ocean, holding the entire structure open against unimaginable pressure. Unlike the violent, crushing collapse found in black holes, a gravastar's core is a realm of serene but potent repulsion. Every cubic centimeter of this vacuum energy exerts an outward push, counterbalancing the relentless gravitational tug of the outer shell. It is a quiet, invisible force, yet it carries the weight of entire stars, sustaining a structure that could endure for billions of years without yielding to collapse. The effect is almost hypnotic. To imagine the interior is to envision a cosmic heartbeat, steady, rhythmic, and unrelenting, a pulse that keeps the shell in perfect suspension. This energy is not turbulence or chaos. It is the universe's own pressure, a subtle current in space-time that stabilizes what would otherwise be an impossible object. Here, gravity is not the ultimate victor. Dark energy asserts itself, pushing outward with a force precisely tuned to the surrounding mass. The gravastar exists because the cosmos allows space itself to resist, to push, and to balance the extremes of matter and motion. This pulsing interior has profound implications for physics. Dark energy, usually thought of as a diffuse force driving the universe's expansion, is concentrated here in a localized, structured form. It forms the core of the gravastar, an energy reservoir so dense yet so perfectly balanced that it prevents singularity formation. Matter approaching the shell encounters a boundary that is simultaneously impermeable and reflective, a layer that channels the influence of the interior outward while maintaining internal equilibrium. The result is an object that is extreme in every sense but mathematically consistent, a tangible embodiment of the universe's ability to maintain order under conditions that would otherwise collapse into chaos. Light and gravitational waves interacting with this pulsating interior carry subtle signatures of its presence. Photons grazing the shell may wobble or orbit momentarily, their paths influenced by the interplay between gravity and the core's repulsive energy. Gravitational waves can reflect faintly, producing echoes that encode information about the core's dynamics, offering observers distant clues to the hidden heartbeat that sustains the gravastar. Unlike black holes, which consume all information that crosses the event horizon, the gravastar's interior preserves a memory of the forces at play, encoded in the fabric of space-time itself. Conceptually, the gravastar is as much a marvel of cosmic engineering as it is a natural phenomenon. It demonstrates that the universe can create structures that defy conventional intuition, objects held open not by ordinary pressure or nuclear reactions, but by the subtle, omnipresent push of dark energy. It is a reminder that even in the most extreme corners of existence, the cosmos finds balance, a pulse that quietly underwrites stability in a realm where destruction would otherwise dominate. In this way, the gravastar becomes more than a stellar remnant. It is a cosmic heartbeat, a rhythm of dark energy that sustains an impossible structure, a testament to the universe's ability to engineer extremes without breaking its own rules. Here, in the quiet pulse of its core, lies the secret of its longevity and the elegant solution to one of physics' most enigmatic puzzles: the persistence of structure in the face of ultimate gravitational collapse. In this model, matter doesn't collapse into a point, it dissolves, transforming into a new state of reality. The core of a gravastar is not a singularity, but a sphere dominated by vacuum energy, a region where ordinary atoms no longer exist, where the familiar rules of matter and chemistry cease to apply. As the star's outer layers fall inward, they are compressed beyond recognition, their constituent particles merging into an exotic, formless energy that fills the interior. It is a metamorphosis of matter into pure structure, a state that is neither solid, liquid, nor gas, but something altogether stranger, a cosmic vacuum stabilized against collapse by the outward pressure of dark energy. This transformation is instantaneous in cosmic terms, yet precise in its mechanics. The gravastar forms when the collapsing mass reaches a critical density, at which point the inward pull of gravity is exactly balanced by the repulsive push of vacuum energy. The outer shell, made of ultra-dense exotic matter, freezes the structure in place, preventing further collapse while preserving the illusion of a horizon. What remains is a sphere that appears from the outside as a black hole, yet its interior is a new phase of reality, a hollow yet stable region where space-time itself behaves differently than anywhere else in the universe. The implications are profound. Matter that once obeyed all familiar laws, nuclear fusion, atomic structure, electromagnetic interactions, has been subsumed into a state dictated entirely by geometry and vacuum energy. Particles, forces, and even light interact with this interior in ways that defy conventional intuition. Photons skimming the shell may orbit, trapped briefly by the extreme curvature of space-time, while gravitational waves reverberate subtly, carrying echoes of the transformation back into the cosmos. In essence, the star's collapse becomes a signal, a ripple through space-time that encodes information about a realm where the ordinary becomes extraordinary. This process also resolves the paradoxes that plague classical black hole physics. A singularity represents a breakdown of mathematical laws, a point where density becomes infinite and predictability vanishes. In the Gravastar model, there is no singularity. The transformation of matter into a sphere of vacuum preserves the continuity of space-time, ensuring that physics remains valid even under extreme conditions. The star does not vanish, it evolves, entering a state that challenges human intuition while remaining fully consistent with theoretical models of gravity and quantum mechanics. Visually, the Gravastar remains a marvel of cosmic illusion. From afar, it casts a shadow nearly identical to that of a black hole, bending light and curving trajectories with deceptive perfection. But inside, it is a realm of subtlety, a sphere of nothingness defined by pressure and energy rather than mass and matter. It is a reminder that the universe can create structures that seem impossible yet are entirely natural, where endings become transformations and collapse becomes a new form of cosmic architecture. In becoming a sphere of vacuum, the star achieves a kind of immortality. Its matter is not destroyed but transmuted, preserved in a new state that defies collapse while maintaining equilibrium. The Gravastar is both an ending and a beginning, a final act in the life of a star that also opens a doorway to a deeper understanding of the universe, where reality itself can take forms that challenge imagination and yet obey the ultimate laws of physics. Photons skim the surface, circling endlessly, like fireflies trapped in a glass globe. Around a Gravastar, light behaves as though caught in a delicate ballet, its path twisted and curved by the extreme warping of space-time near the ultra-dense shell. Unlike a black hole, where photons crossing the event horizon are lost forever, these particles hover at the boundary, trapped in orbit by the delicate balance between gravity pulling inward and the repulsive effects of the vacuum energy beneath. Each photon becomes part of a cosmic choreography, endlessly circling, reflecting the object's presence, while illuminating the strange physics at play. This orbit is not static. Photons can drift in slightly varying paths, some looping many times before eventually escaping, their trajectories stretched and distorted by the shell's extreme curvature. The result is a halo of light that flickers and shimmers in subtle ways, a signature unique to Gravastars. To a distant observer, this ring may appear steady, yet in reality, it is a dynamic, almost living phenomenon, a fleeting, ghostly trace of the intense forces just beneath. The light's last dance is both beautiful and informative, carrying encoded hints of the interior structure, the thickness of the shell, and the pressure of the vacuum energy it contains. The mechanics behind this phenomenon are astonishing. The shell's extreme density bends space around it so sharply that photons entering certain paths are forced into closed loops. The repulsive interior prevents them from spiraling inward to destruction, while the gravitational pull of the shell ensures they cannot escape immediately. This tension creates a region of photon orbit, a halo where light can circle thousands of times, each pass a tiny echo of the Gravastar's invisible heart. In theory, this trapped light could last for eons, a permanent reminder that even in the most extreme environments, energy persists and carries information. Beyond photons, The Gravastar's shell influences other forms of radiation and matter in equally subtle ways. Gravitational waves passing nearby may ripple against the shell, producing faint echoes detectable with sensitive instruments. Neutrinos and other high-energy particles interact with the shell's magnetic and gravitational fields in unique patterns, offering additional clues to the object's structure. Every interaction between the Gravastar and its surroundings is a dialogue, a conversation conducted through the curvature of space, the behavior of light, and the silent pulse of the interior energy. Visually, the effect is mesmerizing. Imagine a ring of fireflies spinning endlessly in a globe of crystal, their movements precise yet unpredictable, illuminating the darkness around them. This is what a Gravastar looks like to light skimming its surface, a halo of frozen motion, a boundary between visible space and the enigmatic void within. It is both a warning and an invitation, a signal that the universe holds structures where light itself can be trapped in perpetual motion, revealing the presence of something extraordinary without ever fully entering it. The dance of photons around the Gravastar is more than a visual spectacle. It is evidence of the object's remarkable balance, a testament to the interplay between gravity, vacuum energy, and the ultra-dense shell. Each orbiting photon is a note in a cosmic symphony, echoing the hidden heartbeat of the Gravastar and offering observers a glimpse of a universe where light can linger, shimmer, and dance indefinitely at the edge of impossibility. The shell may radiate faint thermal light, not from fire, but from the tension of space-time itself. Unlike ordinary stars or planets, the glow of a Gravastar is not generated by nuclear reactions or chemical processes. It emerges from the extreme compression and warping of matter and space at the outer shell, where the forces of gravity and vacuum energy are locked in perfect equilibrium. This energy manifests as a subtle radiation, a ghostly light that hints at the immense pressures contained within, a shimmer born not of heat but of pure cosmic tension. To imagine it is to picture a fire burning without fuel, a luminescence arising from the very geometry of the universe. At the atomic level, the shell is a lattice of exotic matter, compressed so tightly that traditional concepts like electrons and nuclei no longer apply. The burning is a manifestation of the interactions between the shell's structure and the surrounding space-time, producing photons that escape with a faint, almost imperceptible glow. Observing this light is akin to hearing the whisper of a star's heartbeat, a signal of stability and stress encoded in the fabric of the cosmos. This radiation is incredibly faint compared to the searing brilliance of ordinary stars, yet it is a signature that could reveal the presence of a Gravastar. Unlike a black hole, which absorbs nearly all light and energy crossing its event horizon, the Gravastar's shell emits just enough to betray its existence to sensitive instruments. Every photon carries information about the shell's composition, its density, and the extreme forces at play, offering a glimpse into conditions far beyond what is possible in any laboratory. The faint glow becomes a cosmic fingerprint, subtle yet uniquely telling, a direct expression of the balance between inward pull and outward push at the heart of the object. The shell's radiation is also a dynamic phenomenon. As gravitational waves or nearby matter interact with the Gravastar, the tension in the shell fluctuates, producing small variations in the emitted light. Photons may escape more readily along certain paths, or linger longer near the surface, tracing arcs that curve and twist with the space-time around them. In this way, the shell communicates with the universe, radiating not heat but information, an ongoing, luminous dialogue between extreme physics and observation. To the human imagination, this is profoundly alien. A surface that burns without fire challenges our most basic assumptions about energy, radiation, and thermodynamics. It is a realm where the rules of experience fail, where light is produced by stress and structure rather than heat, and where every photon is a messenger from the boundary between matter and the extraordinary. The shell becomes a bridge, a glowing membrane at the threshold of a hollow core that contains forces strong enough to hold entire stars in check. Ultimately, the shell's faint burn is a testament to the Gravastar's ingenuity, nature's ability to sustain extreme objects in perfect equilibrium. It reminds us that the universe is capable of phenomena that appear impossible, yet arise naturally from the interplay of gravity, energy, and geometry. Here, light dances without warmth, matter resists collapse without friction, and the cosmos demonstrates once again that reality is far stranger and more subtle than intuition allows. To an outside observer, the shell appears almost like an event horizon, but it is only mimicry. From a distance, the Gravastar casts a shadow indistinguishable from that of a black hole. Light curves sharply around it, stars orbit in patterns that seem dictated by a singularity, and even gravitational waves respond as if an abyss has formed. Yet no true horizon exists here. The Gravastar's outer shell halts the collapse before any singularity can emerge, creating the illusion of a boundary that swallows everything, a trick of perspective and space-time, a cosmic masquerade. This illusion is subtle yet profound. Photons that approach the shell are bent so sharply that some skim along its surface for extended periods, trapped in orbit by the intense curvature of space. To distant observers, it appears as though these photons are vanishing into an event horizon, but in reality, they are temporarily suspended, circling endlessly around the Gravastar. Even matter that falls close to the shell encounters a barrier, rebounding slightly or oscillating in a way that would be impossible near a true black hole. The horizon exists only as a visual and gravitational deception, a perfect impersonation of a feature that, classically, would mark the ultimate point of no return. The consequences for physics are significant. Traditional black holes erase information beyond the horizon, posing deep challenges for quantum mechanics and the conservation of information. Gravastars, with their pseudo-horizon, preserve the underlying data of infalling matter. Particles, energy, and even the faintest gravitational waves interact with the shell, but are not irretrievably lost. The mimicry maintains appearances while safeguarding the continuity of physical law, offering a solution to paradoxes that have perplexed theorists for decades. The shell's near-horizon behavior also produces fascinating observational phenomena. Light escaping from near the surface can experience extreme redshifts, and the timing of gravitational waves from nearby collisions can reveal minute deviations from black hole predictions. For astronomers armed with high-resolution telescopes and sensitive detectors, these discrepancies are breadcrumbs, subtle clues that differentiate the Gravastar from its more infamous cousin. To identify the true nature of the object, one must look beyond the shadow, beyond the first impression, and study the delicate interplay of forces at the shell's edge. Visually, the pseudo-horizon is mesmerizing. Imagine a mirror reflecting the abyss, a boundary that seems absolute but is in fact a thin, ultra-dense layer holding back a hollow core. It demonstrates the universe's capacity for deception and subtlety, creating objects that simultaneously obey extreme physics and maintain observational illusions. The Gravastar challenges intuition. It is a structure that teaches us not to take appearances at face value, even in the vast, seemingly immutable reaches of space. Ultimately, a horizon that isn't real is a reminder of the cosmos's subtlety. Gravastars show that the universe can produce extreme gravitational phenomena without singularities, can bend light and warp time without violating physics, and can mimic the ultimate abyss while preserving continuity. To the observer, the shell appears as a point of no return, but in reality, it is a testament to balance, structure, and the extraordinary creativity of nature's laws at their most extreme. Time flows strangely near a Gravastar. What looks like the end of a star's life may simply be a transition. To a distant observer, the collapsing star seems to vanish, swallowed by what appears to be an event horizon. Seconds stretch into minutes, minutes into years, as the star's final moments are drawn out by extreme gravitational time dilation. Yet unlike a black hole, where this disappearance signals irreversible collapse into a singularity, the Gravastar offers a different story, a collapse that slows, stretches, and ultimately stabilizes, a transformation rather than an ending. Inside, the vacuum energy of the core pushes outward, countering the relentless inward pull of gravity. This interplay creates a delicate equilibrium where the star never truly disappears, even as it seems to fade from view. For outside observers, The final light dims, photons are stretched to invisibility, and the stellar remnants appear frozen in time. Yet the star itself has not ceased to exist. It has entered a new state, a realm where ordinary measures of time and distance lose their familiar meaning. The death of the star is, in effect, an optical illusion, a temporal trick played by the extreme curvature of space-time near the gravitar. The implications are staggering. What would normally be considered an absolute endpoint, stellar collapse, event horizon, disappearance into nothingness, is here revealed as a continuous process. Time near the shell behaves differently than far away. It slows, stretches, and dilates, making the collapse seem eternal from the outside. But inside the structure, the core pulses with vacuum energy. The shell maintains its integrity, and physics continues uninterrupted. The Gravastar is, in essence, a structure suspended between collapse and stasis, where the end is never final, and the universe preserves continuity even in extremity. This extended collapse produces observational signatures that could, in principle, distinguish gravastars from black holes. Light lingering near the shell experiences extreme redshift, and gravitational waves passing nearby may exhibit subtle echoes or delays, carrying information about the internal equilibrium. The apparent freezing of the star's collapse is itself a signal, a hint that the object is more than a black hole, a celestial enigma where time bends, stretches, and folds without violating the laws of physics. Conceptually, the collapse that never finishes forces a rethinking of stellar death. Gravastars demonstrate that the universe can create conditions where endings are illusions and transformations are masked as conclusions. The star does not vanish, it transitions into a new form, a sphere of vacuum energy bounded by an ultra-dense shell, a structure that balances forces so extreme they would destroy ordinary matter. Time itself becomes part of the illusion, bending around the shell to create the impression of finality, while the star quietly persists. In the end, the Gravastar is a testament to the subtlety of the cosmos. Its collapse is never absolute, its death a mirage, and its existence a reminder that the universe can stretch our understanding of time, matter, and gravity. Here, the final moments of a star are not an ending. They are the beginning of a new, extraordinary form, suspended in the delicate, eternal dance between gravity, vacuum energy, and the flow of time itself. Inside, pressure is not caused by matter but by pure energy pushing everything outward. Unlike the familiar pressure of gas or fluid, generated by particles colliding and jostling, the Gravastar's core is dominated by vacuum energy, an intangible, pervasive force that exerts tension across space-time itself. This energy is the architect of the object, holding the ultra-dense shell at bay and preventing collapse, creating a hollow yet stable interior that challenges everything we assume about gravity and stellar physics. Imagine a bubble whose walls are not made of atoms but of forces, pressure without matter, expansion without substance. The outward push of vacuum energy counteracts the inward pull of gravity so precisely that the Gravastar exists in perfect equilibrium. Even a small imbalance would be catastrophic. Too little energy, and the shell would collapse inward. Too much, and it would expand uncontrollably. Instead, the universe has arranged a balance so delicate that the bubble can persist for billions of years, a floating testament to the interplay between energy, geometry, and cosmic law. This invisible pressure has remarkable consequences for the surrounding environment. Stars orbiting near a Gravastar experience gravitational forces nearly identical to those around a black hole, yet subtle differences arise from the hollow interior. Light and gravitational waves skimming the shell can carry echoes of the internal tension, revealing the presence of a force that has no mass yet exerts influence over everything around it. In this way, the Gravastar is both hidden and revealed. Its shell obscures the interior, yet its pressure leaves signatures detectable by the most sensitive instruments. The physics of this energy-dominated interior is extraordinary. Where a black hole's singularity represents a breakdown of known laws, the Gravastar's core maintains continuity. Space is warped, time is stretched, But no infinities appear, no equations fail. The pressure from vacuum energy is uniform and omnipresent, a cosmic scaffolding that supports the shell, resists gravity, and maintains the object's identity. In essence, the Gravastar demonstrates that energy alone, without matter, can create structure, stability, and even the appearance of mass in its gravitational influence. This invisible bubble also shapes how matter interacts with the object. Material falling toward the shell is not swallowed but gently influenced by the outward pressure, altering trajectories, creating oscillations, and sometimes sending debris back into space. Photons orbit near the shell, trapped in a luminous dance, while gravitational waves echo faintly, carrying subtle information about the forces within. Every observation of a Gravastar is a glimpse into a universe where pressure, not mass, dominates, where energy alone sculpts form and behavior on a cosmic scale. Ultimately, the invisible bubble of pressure is a testament to the universe's subtlety. It shows that structures can exist without traditional matter, that forces we cannot touch or see can hold enormous objects together, and that reality can be far stranger than intuition allows. The Gravastar is not a simple remnant of stellar death. It is a monument to the power of pure energy, a hollow sphere where the cosmos demonstrates that pressure, rather than mass, can govern the fate of stars and the shape of space itself. Some theorists imagine Gravastars as enormous balloons, inflated by the same mysterious force accelerating the universe. This dark energy, usually associated with the expansion of cosmic space on the largest scales, is concentrated here in a finite, structured form. Inside a Gravastar, it acts like a pressurized fluid without substance, a force that pushes outward evenly in all directions, supporting the ultra-dense shell against the pull of gravity. In this view, the Gravastar is not a collapsed star in the traditional sense, but a cosmic bubble, a self-contained object held aloft by the universe's own hidden energy. The analogy of a balloon is more than poetic. The shell is like the rubber membrane of the balloon, incredibly thin yet strong, maintaining the object's shape and integrity. The dark energy inside is the invisible gas, filling the interior with a uniform pressure that counterbalances the immense gravitational forces trying to crush it. Unlike an ordinary balloon, however, this is a structure forged from the fabric of space-time itself. The energy within is not ordinary matter. It is a force intrinsic to the universe, acting everywhere at once, yet concentrated here in a stable, spherical form. This model explains many of the Gravastar's mysterious properties. Light and gravitational waves behave as if near a black hole, tracing paths warped by the shell's mass and the curvature of space. Yet unlike a true singularity, the interior resists collapse, held open by the dark energy pressure. The shell's stability and the hollow core's resistance are two sides of the same cosmic coin. The pressure of vacuum energy inflates the Gravastar from within, preventing the formation of an event horizon while creating the illusion of one to distant observers. It is a cosmic masquerade, a perfectly balanced structure of light, gravity, and energy. The balloon analogy also extends to dynamics. Perturbations, small fluctuations in the shell or surrounding space-time, are absorbed and redistributed by the internal pressure. Maintaining equilibrium, waves of gravitational energy or nearby matter may compress the shell slightly, but the interior pushes back, restoring balance. In this sense, the Gravastar is self-correcting, a dynamic bubble that maintains its form despite external influences, a celestial object both delicate and unyielding. Observationally, this theory predicts subtle differences from black holes. Photons orbiting the shell may linger longer or display faint oscillations, and gravitational wave echoes could reveal the presence of the hollow core. The dark energy balloon concept transforms the Gravastar from a theoretical curiosity into a tangible, testable model, offering a way to reconcile extreme gravity with the preservation of physical laws. Ultimately, thinking of a Gravastar as a cosmic balloon reframes the way we understand matter, energy, and structure. It is a reminder that the universe can produce objects that appear paradoxical, massive yet hollow, dense yet inflated, extreme yet stable. Dark energy, usually considered a distant, abstract force, becomes here the engine of form and balance, inflating a sphere of impossibility that challenges our intuition and expands the boundaries of what is conceivable in the cosmos. At the brink of collapse, quantum effects become strong enough to halt gravity's unstoppable pull. In the final moments of a massive star's death, the forces of gravity grow overwhelming, threatening to compress matter into a singularity where conventional physics breaks down. But in a gravastar, the laws of quantum mechanics intervene, providing a counterforce that prevents infinite density. The core becomes a domain where the probabilistic, discrete nature of quantum reality asserts itself, pushing back against the smooth, relentless pull of gravity and stabilizing the object before a singularity can form. This is not a gentle resistance. Quantum pressure arises from the fundamental principles that govern particles and fields at microscopic scales. The Pauli exclusion principle, which forbids identical fermions from occupying the same state, is amplified under extreme conditions, while vacuum fluctuations create energy that exerts a repulsive effect on collapsing matter. Together, these quantum forces produce a profound macroscopic outcome: a shell that stops collapsing, a hollow interior, and a structure that remains mathematically consistent even under pressures and densities that would otherwise shatter classical physics. The interplay between gravity and quantum mechanics also has observable consequences. Near the shell, space-time is bent so intensely that light is trapped temporarily. Gravitational waves can echo, and particles orbit in complex, non-intuitive paths. These effects are subtle yet measurable, providing potential clues that distinguish gravastars from black holes. Quantum mechanics, usually thought to dominate only at subatomic scales, here dictates the fate of an entire star, demonstrating the universe's capacity to apply microscopic rules at cosmic extremes. This quantum intervention also reshapes our understanding of stellar death. In a black hole, collapse ends in singularity, an ultimate boundary where time and space as we know them cease to function. In a gravastar, however, quantum effects create a boundary without breakdown, a shell where physics remains intact. The collapse is arrested, not destroyed, transforming a star's catastrophic end into a transition to a new state of reality. The star does not vanish, it becomes a gravastar, a hollow sphere stabilized by the very principles that govern the tiniest scales of existence. Conceptually, this is revolutionary. It unites two realms of physics that often appear incompatible: the macroscopic domain of general relativity and the microscopic rules of quantum mechanics. Gravastars suggest that the universe has mechanisms to preserve consistency across scales, using the discrete, probabilistic properties of quantum fields to regulate the extreme, continuous curvatures of space-time. Here, nothing breaks. Instead, nature adapts, creating structures that obey both the rules of the very large and the very small. Ultimately, quantum physics at the brink of collapse is a cosmic safeguard. It halts gravity's ultimate assault, preserves the integrity of physical law, and allows a gravastar to exist as a stable, hollow object that mimics black holes while maintaining internal consistency. It is a reminder that even in the most extreme corners of the universe itself enforces balance, applying subtle, fundamental principles to create order from the brink of chaos. In the realm of gravastars, quantum mechanics is not optional. It is the architect that ensures collapse never reaches the impossible, providing the invisible hand that sculpts reality at its most extreme. This boundary may be composed of a substance that doesn't exist anywhere else in the universe, a form of matter with negative pressure. Unlike the atoms and molecules familiar on Earth, this exotic matter is a product of extreme physics, a material whose properties defy intuition. It can resist the crushing pull of gravity not by rigidity or density alone, but by exerting an outward tension, effectively pushing against the collapse that would otherwise form a singularity. The shell is both barrier and scaffold, an ultra-thin membrane that contains the hollow interior while shaping the gravastar's interaction with the outside universe. Negative pressure is a concept almost alien to everyday experience. While ordinary matter resists compression by bouncing back when squeezed, exotic matter creates tension, pulling outward as if the shell itself was striving to expand. This tension balances the inward crush of gravity with uncanny precision, holding the core open and preventing collapse. The result is a stable, long-lived object where space-time is warped to extremes, light is bent into looping paths, and gravitational waves carry echoes of the shell's extraordinary rigidity. The exotic matter also transforms the nature of the Gravastar's surface. Unlike a conventional star or planet, which radiates due to heat, the shell's properties allow it to emit subtle light and energy purely from the stresses of spacetime itself. Photons orbit near the boundary, caught in loops by the curvature of space and the shell's influence, creating luminous rings that hint at the exotic forces at play. To an observer, the shell may appear calm and silent, but in reality, it is a structure of immense tension and balance, quietly maintaining the interior against the universe's most extreme forces. This material's existence also has deep theoretical implications. Exotic matter with negative pressure is precisely the type of substance required to reconcile general relativity with quantum mechanics in extreme environments. It provides a mechanism for stabilizing objects that would otherwise collapse, suggesting that the universe has ways of preserving continuity and order even under the most extreme conditions. The Gravastar's shell becomes a laboratory in principle, a place where the rules of energy, pressure, and space-time converge to produce a phenomenon that is otherwise impossible in ordinary conditions. Despite its thinness, the shell dictates the Gravastar's behavior. Every photon, every orbiting particle, every passing gravitational wave interacts with this layer, revealing subtle clues about its composition and properties. Its negative pressure is what allows the interior vacuum energy to dominate, creating a hollow yet stable core. It is both guardian and signature, the defining feature that differentiates a Gravastar from a black hole while remaining almost invisible to conventional observation. Ultimately, the shell made of exotic matter embodies the elegance of extreme physics. It demonstrates that the universe can create materials and structures beyond ordinary experience, objects that survive and function under conditions that would destroy anything familiar. It is a boundary of tension, a surface of impossibility, and a testament to nature's ability to craft stability out of forces that, by ordinary intuition, should tear everything apart. The Gravastar's exotic shell is the key to its identity, the invisible hand that holds open a hollow heart in the universe's most extreme corners. The interior pushes outward so strongly that it resists collapse, holding the entire structure in perfect balance. At the heart of a Gravastar lies not matter in any familiar form, but a seething reservoir of vacuum energy, a force that acts like anti-gravity, countering the crushing pull of the outer shell. Whereas ordinary stars are dominated by the tug of gravity drawing everything inward, the Gravastar is defined by the equal and opposite push from within, a pressure so immense yet so uniform that it prevents the formation of a singularity, stabilizing the object in a state of exquisite equilibrium. This core is a paradox of nature. It is simultaneously empty and full, a void that exerts tangible influence over everything around it. Light that grazes the inner boundary of the shell is deflected, trapped briefly in orbit before escaping, while gravitational waves echo faintly, carrying information about the core's energy and structure. Unlike a black hole, which consumes everything that crosses its horizon, the Gravastar preserves its interior integrity, resisting the pull of gravity with a force that is almost unimaginable in scale. The anti-gravity effect arises from the unusual properties of vacuum energy, which behaves differently than ordinary matter. In normal circumstances, energy density and pressure combine to produce gravitational attraction. But in the Gravastar's core, negative pressure dominates, generating an outward push that grows stronger as the shell compresses inward. The balance is self-regulating. The harder gravity pulls, the stronger the core pushes back, producing a dynamic equilibrium that can last for billions of years. It is a cosmic counterweight, a force of nature that stabilizes what would otherwise be a catastrophic collapse. This outward push also shapes the shell and the surrounding spacetime. The Gravastars' photon ring, its subtle halo of orbiting light, is influenced by the delicate tension between inward gravity and outward pressure. Photons can circle the shell many times, and gravitational waves passing nearby may reflect faintly, encoding the signature of the anti-gravity core. Every interaction with the Gravastar carries the imprint of this invisible push, offering distant observers hints of the extraordinary forces at play within. Conceptually, the anti-gravity core challenges our intuition. Gravity, normally the ultimate destroyer, is here held in check by an invisible, omnipresent energy. A structure that would otherwise collapse into oblivion is stabilized by a force that defies ordinary experience, demonstrating that the universe has mechanisms to preserve equilibrium, even under its most extreme conditions. The core is both a source of stability and a beacon of cosmic ingenuity, revealing how matter and energy can organize into forms that are almost miraculous in their resilience. Ultimately, the anti-gravity core is the Gravastar's secret, the hidden engine that maintains balance, preserves structure, and defies the universe's most extreme destructive tendencies. It is a hollow yet potent heart, an interior that pushes outward with the same intensity that gravity presses inward, a force of equilibrium that allows the Gravastar to exist as a perfect synthesis of tension, structure, and cosmic law. Here, in this anti-gravity sanctuary, the universe demonstrates that stability can arise not from mass alone, but from the careful interplay of pressure, energy, and geometry at the edge of physical possibility. Some physicists argue that every so-called black hole is actually a Gravastar in disguise, a cosmic switcheroo. To distant observers, the two are virtually indistinguishable. Both bend light, tug on nearby stars, and generate gravitational waves that ripple across the cosmos. Yet, hidden beneath the shadow of the apparent event horizon, a Gravastar's interior is a world entirely unlike a black hole's singularity. Where classical theory predicts points of infinite density and the destruction of information, the Gravastar preserves structure, energy, and the very laws of physics. This idea challenges everything we think we know about stellar death. For decades, black holes have been considered the ultimate endpoint of massive stars, objects so extreme that nothing could escape their grasp. Yet if Gravastars are the true occupants of these cosmic locations, then the universe has been hiding a secret, a way to mimic the appearance of absolute darkness while maintaining internal order. Each observed black hole may be less a cosmic trapdoor and more a hollow, energy-driven bubble, a structure of extraordinary precision that has fooled generations of astronomers. The observational consequences of this theory are subtle yet profound. Gravastars can reproduce nearly all the gravitational effects attributed to black holes, lensing of light, orbital motion of nearby stars, and even the echoes of colliding massive objects. But there are slight differences: photon rings that linger longer, gravitational wave echoes that persist faintly, and signals from matter interacting with the shell rather than vanishing into a singularity. With increasingly sensitive instruments, scientists hope to detect these distinctions, peeling back the illusion and revealing whether the universe truly prefers hollow cores over singularities. Philosophically, the concept is stunning. A Gravastar masquerading as a black hole is a reminder that appearances can deceive, even on the grandest cosmic scales. The universe can create objects that fulfill expectations in one sense while subverting them in another. Gravity behaves as if a black hole exists, yet quantum effects, exotic matter, and vacuum energy conspire to prevent the singularity, preserving information and maintaining continuity. The cosmos becomes not a realm of destruction, but a stage for subtle engineering, where extreme physics operates in perfect disguise. If all black holes were actually Gravastars, many of the paradoxes of modern astrophysics would vanish. The information paradox, which challenges the conservation of information when matter falls into a black hole, would dissolve. Singularities, which break down the predictive power of physics, would be replaced by stable cores of vacuum energy. The universe, rather than harboring points of ultimate destruction, would be home to structures that are extreme yet fundamentally coherent, hollow yet gravitationally convincing, exotic yet entirely lawful. Ultimately, the idea that black holes might not exist is not a denial of gravity, mass, or the extremes of stellar evolution. It is a revelation that the cosmos has more subtlety than we often assume. Gravastars are a testament to nature's ingenuity, objects that imitate the ultimate abyss while preserving internal order. Structures that teach us that the universe can bend expectations, maintain balance, and create mysteries so convincing that even centuries of observation can be fooled. The cosmic switcheroo is complete. What we thought was the end may, in fact, be a hollow beginning. A silent, energy-driven heart masquerading as darkness itself. Instead of disappearing, infalling matter may smear across the shell like paint on a drum, adding to its mass. In a black hole, anything that crosses the event horizon is lost forever, vanishing into a singularity from which no information can escape. A gravastar, however, behaves differently. Its ultra-dense shell is a barrier that halts the final descent of matter, forcing it to spread across the surface rather than being destroyed. Colliding with the shell, the material is absorbed gradually, increasing the overall mass of the object while leaving its interior untouched. This process is violent yet controlled. Matter approaching the shell is subject to extreme tidal forces, stretched, compressed, and warped as it interacts with the curvature of space-time. It cannot penetrate the vacuum energy core, so it flows along the boundary, distributing itself across the surface. The shell's exotic matter accommodates this addition with a remarkable resilience, absorbing energy and mass while maintaining equilibrium. In effect, the gravastar grows from the outside in, a living structure that evolves incrementally as it interacts with its environment. The interaction of infalling matter with the shell produces observable phenomena. Material scraping along the surface can emit faint radiation, not from heat in the traditional sense, but from the stress and deformation of space-time itself. Photons and gravitational waves generated during this process can escape, carrying subtle clues about the shell's composition, the internal pressure of the core, and the extraordinary forces at play. To an observer, the gravastar may seem to be accreting mass in a familiar way, but the details, orbital dynamics, light echoes, and gravitational signatures hint at something fundamentally different from a classical black hole. This smearing process also preserves information. Unlike a singularity, which erases the history of infalling matter, the gravastar's shell acts as a record, storing mass and energy without violating the laws of quantum mechanics. Infalling particles leave their imprint on the shell, and, in principle, the information they carry could be recovered, albeit indirectly. The universe thus avoids the paradoxes of destruction, maintaining continuity even as matter is added to an extreme, energy-dominated object. The process is both a visual and conceptual marvel. Imagine paint dropped on a taut drumhead. Each droplet spreads, ripples outward, and becomes part of a coherent, dynamic surface. The gravastar's shell behaves similarly, absorbing the incoming material while remaining intact, preserving its hollow interior and anti-gravity core. The addition of mass does not compromise stability. Instead, it demonstrates the object's self-correcting equilibrium, the delicate balance between gravity and vacuum energy, inward pull and outward push. Ultimately, what happens to matter that falls in transforms our understanding of cosmic extremes. Gravastars show that the universe can recycle, redistribute, and preserve material rather than destroy it. Infalling stars, dust, and gas become part of the shell's structure, contributing to its growth while leaving the core pristine. It is a process both alien and elegant, revealing that even at the edge of physics, the cosmos favors continuity, balance, and subtlety over the brute finality of singularities. Nothing inside reaches the core. The center remains a pristine void filled only with energy. In a gravastar, the core is not a destination but a boundary, a region of pure vacuum energy that resists any intrusion. Matter falling inward, photons orbiting the shell, and even the most energetic particles are stopped before they reach the heart of the object. The interior remains untouched, a hollow sanctuary where the forces of the universe are held in perfect equilibrium, maintaining a state of cosmic balance that defies the expectations of conventional stellar physics. This pristine core is sustained by the interplay between the outward push of vacuum energy and the inward pull of gravity. The anti-gravity effect of the core exerts a repulsive force so strong that it prevents matter or radiation from penetrating. The shell, composed of exotic matter, mediates this interaction, absorbing energy and momentum while keeping the interior intact. No matter, no light, and no information crosses into the heart itself. Everything skirts the edges, trapped in orbits, or smeared across the shell, leaving the center as a perfect, untouched void. The consequences are profound. Unlike a black hole, where the singularity is a destructive point that annihilates everything that falls in, the Gravastar preserves the core as a pristine reservoir of energy. This vacuum energy heart serves as the stabilizing engine of the entire structure. It exerts uniform pressure outward, maintaining the shell's shape and preventing collapse. It also ensures that time and space remain continuous within the object, eliminating the infinities that plague classical black hole theory. In essence, the Gravastar is a star that never truly dies, a stellar remnant suspended in a state of eternal equilibrium. Photons and gravitational waves interacting with the shell provide hints about the hidden interior, yet the core itself remains inaccessible. Light can circle endlessly near the boundary, and matter can orbit the shell. But the central void is inviolate. Even extreme events, like collisions with other massive objects or bursts of infalling material, cannot breach the interior. The center is a sanctuary of energy, a hollow engine driving the Gravastar's existence without ever being touched. Conceptually, this challenges intuition. We are accustomed to thinking of stars, planets, and collapsed objects as having interiors filled with matter. In a Gravastar, the interior is an absence, yet it is precisely this absence that defines the object. The core's emptiness is active, generating the outward pressure that stabilizes the shell and governs the behavior of everything that approaches. It is a void that has agency, a space defined not by what it contains, but by the forces it exerts on its surroundings. Ultimately, the star that never touches its center is a radical vision of cosmic architecture. It is a reminder that the universe can create stability from emptiness, structure from absence, and balance from what seems like nothing. In this hollow heart lies the secret of the Gravastar's enduring mystery, a pristine, untouchable core of pure energy, sustaining a shell of exotic matter and allowing the universe to hold an extreme object in perfect equilibrium, where collapse is halted and physics remains unbroken. A Gravastar is not solid or liquid or gas. It is emptiness contained by impossibility. Unlike any object familiar to our experience, its interior is a void, a hollow sphere filled not with matter but with vacuum energy, a form of energy that resists compression and pushes outward with relentless uniformity. It is a space that has no substance in the traditional sense, yet its influence shapes everything around it: the orbit of photons, the motion of nearby stars, and the curvature of space-time itself. The Gravastar's interior is a paradox, a region where the absence of matter creates structure, and emptiness holds more power than anything tangible. This hollow core is stabilized by the delicate tension between the outward push of vacuum energy and the inward pull of the ultra-dense shell. The exotic matter of the shell forms a perfect boundary, containing the void without collapsing, warping, or yielding. The forces at work are extreme. Gravity attempts to pull inward, vacuum energy presses outward, and space-time itself is stretched and curved into forms that challenge our understanding of geometry. In this impossible balance, the Gravastar becomes a self-sustaining structure, a hollow object that exists because the universe permits extremes beyond everyday intuition. Matter that falls toward the Gravastar never enters the hollow interior. It collides with the shell, smears across its surface, and contributes to the object's mass, but the core itself remains untouched, a pristine void governed solely by energy. Light, too, cannot penetrate this emptiness. Photons skim the shell, trapped temporarily in orbit by the curvature of space-time, creating luminous rings and halos that reveal the presence of the hollow interior without ever allowing direct access. Even gravitational waves interact with the shell and the surrounding space-time, but the interior itself is impervious, a vacuum so pure that it contains no singularity, no atoms, and no conventional energy. The implications for physics are staggering. A hollow interior removes the paradoxes of infinite density and information loss that plague classical black hole models. Time and space remain continuous, and the laws of physics continue to hold even at the most extreme scales. The Gravastar demonstrates that the universe can organize emptiness into a stable, structured object, showing that nothing can be just as consequential as something. In this sense, the hollow interior is not a weakness or a gap, it is the defining feature that allows the Gravastar to exist at all. Conceptually, it is a revelation. We are trained to think of objects in terms of substance, solid cores, liquids, gases, but here is a star that is almost entirely absence, yet produces gravity, light effects, and observable phenomena identical to the most extreme stars in the universe. The hollow interior embodies the poetry of physics, a void held by impossibility, a space of pure energy that defies intuition, yet shapes reality with precision. Ultimately, the Gravastar's hollow interior is a reminder that the universe operates on principles far stranger than our daily experience. It is a sanctuary of vacuum energy, a void contained by the tension of space-time, and a structure that exists in defiance of ordinary expectation. It shows that emptiness, when harnessed by extreme physics, can become as powerful and consequential as the densest matter, producing a cosmic object that is simultaneously fragile, impenetrable, and perfectly balanced, an impossibility made real. Without a singularity, they might not emit Hawking radiation the same way black holes do, making them effectively immortal. Black holes are thought to slowly lose mass over eons, radiating energy from the edge of their event horizons in a process predicted by Stephen Hawking. This radiation is intimately tied to the existence of a singularity, a point of infinite density that warps space-time so intensely that quantum effects create particle-antiparticle pairs at the horizon, some of which escape, slowly draining the black hole. Gravastars, however, have no singularity to anchor this process. Their hollow, energy-filled interior and ultra-dense shell do not produce the same conditions for Hawking radiation to form. The result is remarkable. Gravastars may persist indefinitely. Without a mechanism to shed energy in the form of radiation, they do not evaporate over time. Instead, they remain as stable, long-lived objects, their structure maintained by the outward push of vacuum energy and the containment provided by exotic matter in the shell. In essence, they are cosmic fortresses of equilibrium, objects that resist change not through resistance to outside forces alone, but by fundamentally lacking the features that would allow decay. Where a black hole is a ticking clock, slowly bleeding away mass and approaching eventual disappearance, a Gravastar could remain unchanged for billions, even trillions of years. This stability has profound implications for astrophysics and cosmology. If Gravastars populate the universe instead of black holes, then the end stages of stellar evolution are not destructive but conservative. Matter and energy are preserved in ways that do not violate quantum mechanics, and the information paradox, the puzzle of whether information is lost in a black hole, is sidestepped entirely. Gravastars do not swallow information irreversibly. They store it on their shell or allow it to interact with the surrounding universe, meaning that the laws of physics remain intact. The lack of evaporation also affects the observational signatures of Gravastars. Over cosmic timescales, they maintain their mass and gravitational influence, leaving behind persistent effects on nearby stars, orbital systems, and light paths. Photon rings, gravitational wave echoes, and interactions within falling matter remain consistent, unlike black holes, whose gradual mass loss alters their surroundings over aeons. In this way, a Gravastar is not only stable internally but also externally, providing a lasting footprint in the cosmos. Conceptually, the immortality of Gravastars is astonishing. They represent a class of objects where extreme gravity and exotic physics combine to produce permanence rather than decay. A hollow interior, a shell of exotic matter, and a core of vacuum energy form a structure that is effectively timeless, an object that can outlive galaxies, persist across cosmic epochs, and remain an enduring fixture in the universe. Unlike stars that burn out or black holes that slowly vanish, gravastars are the universe's long-term survivors, a testament to the subtle interplay between quantum mechanics, relativity, and exotic energy. Ultimately, why gravastars don't evaporate is more than a technical detail. It is a statement about the nature of permanence and stability in the cosmos. These objects defy the expectation of decay, demonstrating that the universe can produce extreme entities that endure not through resistance to destruction, but through the absence of mechanisms that would allow it. Gravastars are, in a very real sense, immortal monuments to the laws of physics, eternal witnesses to the vast, unfolding story of the cosmos. If gravastars exist, their gravitational waves might return faint, delayed whispers, space-time bouncing against their shell. Unlike black holes, which absorb nearly all perturbations that cross their event horizons, gravastars possess a rigid, ultra-dense shell surrounding a hollow core. When a massive object collides with or orbits near a gravastar, the resulting ripples in space-time, the gravitational waves, interact with this boundary, reflecting and reverberating in ways that create subtle, delayed signals. These echoes are the gravastar's signature, a gentle yet persistent communication from an object that seems like silence from afar. The physics behind these echoes is extraordinary. Gravitational waves carry energy through the fabric of space-time itself, stretching and squeezing it as they pass. Near a gravastar, the hollow interior and the shell's extreme stiffness prevent full absorption. Waves that would vanish into a black hole instead linger, bouncing internally, producing a faint, repeating pattern that slowly radiates outward. To a distant detector, such as LIGO or Virgo, these echoes would appear as tiny repetitions or distortions in the expected signal of a massive collision, hinting at the presence of a structure unlike any conventional object. The implications are profound for observation. If we detect such echoes, they could provide the first direct evidence of gravastars, distinguishing them from black holes. The timing, amplitude, and frequency of the returning waves encode information about the shell's density, thickness, and rigidity, as well as the energy of the hollow core. It is as if the gravastar is ringing after being struck, a cosmic bell whose sound is almost imperceptible but carries the secrets of its exotic interior. These echoes also reveal something philosophical about the nature of the universe. Black holes are silent, absolute endpoints where information disappears. Gravastars, by contrast, preserve and reflect. The returning waves are a form of communication, a whisper from the cosmos that confirms structure, continuity, and the preservation of physical law. Matter, energy, and gravitational disturbances are not swallowed irreversibly. They interact with the shell and then propagate outward, leaving traces that could be read by sensitive instruments. The universe, in this sense, is not hiding its gravastars. It is signaling their existence through subtle vibrations in space-time. Moreover, these echoes are a window into extreme physics. They show how vacuum energy, exotic matter, and the interplay of inward and outward forces create objects that behave unlike anything we can replicate in a laboratory. Each wave carries the imprint of the core's anti-gravity push and the shell's tensile strength, giving astrophysicists a rare glimpse into a regime where relativity and quantum effects converge. In the gentle delay of a gravitational whisper, we may witness the universe's most delicate balancing act. Ultimately, echoes, instead of silence, is a poetic and scientific hallmark of gravastars. Where a black hole devours and forgets, a gravastar responds and preserves, leaving behind faint whispers of its structure and existence. These echoes are the universe speaking in the quiet language of space-time, a testament to objects that defy collapse, endure indefinitely, and reveal that even in the darkest corners, The cosmos can be unexpectedly communicative. Some theories propose that gravastars reflect certain energies instead of absorbing them, like mirrors made of gravity. Unlike black holes, which act as ultimate sinks, swallowing light, matter, and energy without return, gravastars may interact with their surroundings in a far more subtle and intriguing way. The hollow interior, bounded by a shell of exotic matter and stabilized by vacuum energy, can bounce incoming gravitational waves, photons, or high-energy particles, producing faint but detectable reflections. In essence, a gravastar may behave like a cosmic mirror, turning the universe's own forces back upon themselves. The concept challenges conventional ideas about extreme astrophysical objects. When light or gravitational waves approach the shell, the intense curvature of space-time and the properties of exotic matter can prevent total absorption. Instead, part of the energy is reflected, delayed, and sometimes distorted, creating patterns that ripple outward across space. These reflections could carry the fingerprints of the gravastar's interior, the density of the shell, the distribution of vacuum energy, and the anti-gravity effect of the core. Observationally, these effects would be subtle: a faint shimmer, a tiny echo, a minor deviation in the expected path of a passing photon, but they offer a tantalizing method to distinguish gravastars from black holes. The mirror-like behavior extends to gravitational waves as well. When two massive objects, such as neutron stars or black holes, or possibly gravastars themselves, interact in close proximity, space-time ripples are sent outward. In the presence of a gravastar, some of these waves might reflect off the shell, creating echoes that travel back toward detectors on Earth. The delay and modulation of these waves could reveal the structure and properties of the shell and core, providing direct evidence for the existence of these extraordinary objects. It is as if the universe has built an observatory into the gravastar itself, allowing its internal composition to be probed without breaking the laws of physics. The cosmic mirror hypothesis also carries profound philosophical implications. Whereas black holes represent ultimate destruction and information loss, gravastars preserve, reflect, and respond. Incoming energy is not irreversibly consumed. It interacts, carries away information, and leaves subtle signatures in the surrounding cosmos. In a sense, gravastars are communicative objects, reflecting the universe back upon itself and offering clues to those who know where and how to look. The universe becomes not merely a stage for extreme gravity, but a reflective medium, where energy and information bounce and resonate rather than vanish. Conceptually, a gravastar as a cosmic mirror underscores the object's elegance. It is a structure of paradoxes, hollow yet massive, empty yet influential, invisible yet reflective. Light, matter, and gravitational waves are sculpted by the shell's properties, responding to forces that are both familiar and alien. Each reflection is a message encoded in physics, a subtle reminder that the cosmos has mechanisms for continuity, balance, and observation, even in its most extreme corners. Ultimately, the cosmic mirror hypothesis transforms the gravastar from a passive object into an active participant in the universe. It demonstrates that the most extreme structures may not simply consume reality. They can interact with it, preserve it, and reflect it, producing a dialogue between forces, energy, and observers. In these faint, gravitational, and photonic echoes, the universe hints at its most hidden and elegant truths. Astronomers now listen for subtle signatures, hints in starlight, gravitational waves, and shadow shapes. The hunt for gravastars has transformed the way we look at the universe, pushing technology and imagination to their limits. Unlike conventional black holes, which announce themselves with predictable effects on nearby matter, gravastars demand scrutiny at the edge of detectability. Every photon, every ripple in space-time, and every orbital anomaly becomes a potential clue, a whisper that could reveal the presence of a hollow, energy-filled object masquerading as darkness. Modern observatories, from gravitational wave detectors like LIGO and Virgo to radio telescopes capturing precise stellar orbits, are tuned to catch these faint signals. A tiny deviation in a star's path, a lingering photon ring, or a delayed gravitational echo could point to the existence of a gravastar. Astronomers look for anomalies in the way light bends around massive objects, for the subtle differences in how waves interact with a shell rather than a singularity. Each data point is a potential footprint of something extraordinary, a structure that defies the laws we have long considered absolute. The challenge is immense. Gravastars are designed by the universe to imitate black holes, and their signatures are almost indistinguishable from their more conventional cousins. Detecting one requires extreme sensitivity and careful analysis, teasing out echoes from background noise, measuring minuscule distortions in starlight, and comparing patterns of gravitational waves with models that include hollow interiors and exotic shells. It is a cosmic detective story, where the clues are subtle, the suspects are massive, and the consequences of discovery are profound. Yet the pursuit itself has driven innovation. New imaging techniques aim to map the shadow cast by supermassive objects in unprecedented detail. Instruments capable of detecting faint thermal radiation or unusual orbital dynamics provide indirect glimpses of the shell and core. Even the tiniest signals, slight delays in gravitational waves or faint oscillations in light rings, could confirm a gravastar's presence. By listening for these nearly imperceptible hints, astronomers are stretching the limits of observational physics, testing both theory and technology against the universe's most extreme environments. The philosophical significance is equally remarkable. Searching for gravastars is not just a quest for exotic objects. It is a test of our understanding of reality itself. If detected, these objects would challenge the very idea of singularities, event horizons, and the finality of stellar collapse. They would demonstrate that nature can maintain structure where we expect destruction, preserve information where we anticipate loss, and create stability in the most extreme conditions. Observatories become more than instruments. They are translators, decoding the faint signals of the universe to reveal what is otherwise invisible. Ultimately, observatories searching for the impossible embody humanity's curiosity and persistence. They listen to the quiet echoes of space-time, trace the subtle shimmer of starlight, and scrutinize the shapes of shadows, all in pursuit of a profound question: does the universe hold objects that exist at the edge of physics, structures that imitate black holes while preserving the laws of reality? In every subtle signature, every delayed wave, and every faint reflection, astronomers seek the answer, inching closer to glimpsing the impossible, hollow, eternal, and extraordinary gravastars that challenge our understanding of the cosmos. Some gravitational wave events show patterns that do not align perfectly with black hole predictions. On certain occasions, LIGO, Virgo, and other detectors have captured ripples in space-time that behave in ways slightly off from the expected signature of merging black holes. The waves lingered a fraction longer, oscillated with subtle anomalies, or contained faint echoes that seemed to bounce after the main event had passed. For physicists and astronomers, these deviations were tantalizing, a hint that something extraordinary might be lurking behind the mask of darkness. The anomalies were not random noise. They appeared consistently enough to demand attention. A merger that should have produced a clean, decaying wave instead left behind residual vibrations, tiny reverberations that suggested an internal structure capable of reflecting or delaying the passage of energy. The conventional model of black holes, with their event horizons and singularities, could not account for these lingering signals. Yet the gravastar hypothesis offered an intriguing explanation. The hollow interior and rigid, exotic shell could produce precisely the kind of faint echoes detected, turning LIGO's instruments into cosmic ears that had just caught a whisper from an object unlike anything previously confirmed. The detection immediately sparked debate. Could the anomalies be explained by noise, or by a more conventional astrophysical process? Every possible explanation was considered and ruled out one by one. The pattern, timing, and shape of the echoes hinted at a hollow structure capable of reflecting gravitational waves, an impossible feature for a classical black hole. The Gravastar model, once theoretical and almost purely speculative, suddenly became a viable candidate, offering a framework to interpret data that had previously confounded researchers. What makes these events remarkable is their subtlety. Unlike visible light, gravitational waves travel vast distances unimpeded, carrying unaltered information about the cataclysmic events that generated them. Detecting an unexpected pattern in these waves is akin to hearing a faint whisper across the expanse of the universe. It requires precision, patience, and the ability to read the smallest distortions against a backdrop of cosmic activity. LIGO's sensitivity to these anomalies opens a window into the extreme physics of gravastars. Their anti-gravity cores, exotic shells, and hollow interiors all leave detectable fingerprints, encoded in the very fabric of space-time. The implications of such a discovery are staggering. If confirmed, these signals could rewrite our understanding of stellar death, gravitational collapse, and the fate of matter under extreme conditions. The universe may be populated not with singularities, but with hollow, energy-driven structures that imitate black holes while preserving the laws of physics. Gravastars would become living laboratories for the study of quantum gravity, exotic matter, and vacuum energy, offering insights into regimes of the cosmos previously thought unreachable. Ultimately, the day LIGO detected something strange is a testament to the universe's subtlety and our own ingenuity. It reminds us that the cosmos is capable of surprises, that objects may exist in forms that challenge intuition, and that by listening carefully to the faintest echoes in space-time, we may glimpse the impossible. Gravastars, long theoretical, are suddenly not just a speculation. They are a candidate for the shadows we see in the sky, a possibility that the universe continues to guard its most extraordinary secrets with the quiet language of waves and echoes. A gravastar's outer boundary may vibrate after cosmic collisions, sending faint tremors across the universe. Unlike a black hole, which swallows all disturbances without returning a trace, the gravastar's exotic shell can resonate when struck by infalling matter, gravitational waves, or the tidal forces of nearby stars. These vibrations are subtle yet persistent, rippling outward like the reverberations of a massive drumhead, carrying encoded information about the shell's density, thickness, and the energy of the hollow interior. The physics behind this cosmic percussion is extraordinary. When a neutron star, asteroid, or cloud of gas collides with the shell, the impact does not penetrate the hollow interior. Instead, the shell flexes under the strain, oscillating with the tension provided by exotic matter and the outward push of vacuum energy. The vibrations create secondary gravitational waves, tiny, delayed echoes that travel across space-time. These tremors are faint, often lost in the background noise of the cosmos. Yet with sensitive instruments, they may be detected and analyzed, revealing the hidden architecture of an object otherwise invisible. This drumbeat is both violent and elegant. Matter smears across the shell like paint on a taut membrane, transferring energy without destabilizing the gravastar. The anti-gravity core ensures the hollow interior remains pristine, while the shell responds dynamically, flexing and ringing without fracturing. In effect, the gravastar becomes a self-contained musical instrument, each collision producing unique patterns of vibration that encode its mass, rigidity, and internal pressure. No two impacts produce identical rhythms. Each is a fingerprint of the shell's extraordinary physics. Observationally, these vibrations may offer some of the clearest evidence for gravastars. While photon rings, gravitational wave echoes, and shadow shapes provide indirect hints, the drum-like oscillations offer a dynamic signature that is difficult to replicate with conventional black holes. Detecting these subtle tremors could allow astronomers to map the shell's properties with unprecedented precision, measuring the tension of exotic matter and inferring the energy density of the hollow core. In this way, the universe itself becomes a laboratory, with the gravastar's shell as the experimental apparatus. Conceptually, the idea of a shell that rumbles like a drum is breathtaking. It is a tangible demonstration of how extreme physics manifests on cosmic scales, hollow yet massive, delicate yet unyielding, responsive to external forces, while preserving internal stability. The Gravastar is not inert. It interacts with its environment, communicating through vibrations that traverse light years. The shell's music is a form of cosmic storytelling, a way for these extreme objects to leave traces of their existence across the universe, long after the initial collision has passed. Ultimately, the drumbeat of a Gravastar is a reminder that the universe is alive with subtle motion, that even the most extreme objects respond to interactions in ways that are measurable, meaningful, and profoundly beautiful. These faint tremors are both signals and poetry, proof that the cosmos, even in its darkest, most extreme corners, is a place of rhythm, resonance, and enduring structure. The Gravastar's shell does not merely contain energy, it sings it, ringing across space-time in a testament to the harmony hidden within the extremes of physics. Where black holes roar with radiation and jets, Gravastars remain eerily quiet, cosmic predators that never howl. A black hole announces itself with luminous accretion disks, blazing X-rays, and powerful jets that pierce galaxies, signaling its presence across light years. Gravastars, in contrast, betray almost no outward fanfare. Their hollow interiors, anti-gravity cores, and exotic shells allow them to interact with matter and energy while emitting barely a whisper. To the universe, they are shadows in the dark, objects of immense influence that remain mysteriously still. This silence is not weakness, it is precision. The shell of exotic matter absorbs in falling material without igniting violent radiation, and the hollow core prevents singularity-driven effects from creating extreme energy outbursts. Light can skim the shell, photons can orbit temporarily, and gravitational waves can echo faintly. But none of these produce the violent cosmic noise we associate with black holes. In effect, Gravastars are predators of a subtler kind. They bend space-time, trap matter, and influence their surroundings without the dramatic pyrotechnics, achieving the same gravitational dominance while remaining almost invisible to traditional observational methods. The quiet nature of Gravastars has profound observational consequences. Astronomers relying on high-energy emissions to locate black holes might overlook Gravastars entirely. These objects lurk in the dark, detectable only through their effects on orbiting stars, subtle gravitational wave echoes, or tiny distortions in starlight. Their influence is pervasive yet understated, like a predator stalking its prey silently, detectable only through the movement it causes in others. It is a cosmic game of hide and seek, where the Gravastar's mastery lies in its ability to remain unnoticed while exerting tremendous power. This silence also reflects the internal physics of Gravastars. The exotic shell and anti-gravity core create stability that precludes the violent energy release typical of accretion around black holes. The hollow interior prevents matter from reaching a singularity, so the extreme heating and jet formation that produce the roar of black holes never occur. Gravastars are extreme in mass and influence, yet their extremity is expressed through restraint. The universe provides them with the tools to dominate, yet they operate almost invisibly, bending the rules of what we expect from cosmic monsters. Philosophically, the monster made of silence challenges our notions of power and visibility. Gravastars demonstrate that influence does not require noise, that dominance can exist without spectacle, and that the most extreme objects in the universe need not announce themselves with drama. Their quietude is a testament to the balance between vacuum energy, exotic matter, and space-time curvature, showing that the universe can produce objects of immense strength that remain elegantly restrained. Ultimately, Gravastars are predators that never howl. They are masters of silence, shaping galaxies and warping space-time with invisible hands. Their existence, if confirmed, would reveal that the cosmos harbors extremes beyond imagination, where power and subtlety coexist, and where the loudest effects are sometimes the least revealing. In the stillness of a Gravastar, the universe hides its most enigmatic and enduring creations, reminding us that silence can be as profound as the roar of a collapsing star. Time nearly stops at the shell, stretching moments into eternities, creating a boundary between the real and the unreachable. To an outside observer, The Gravastar appears frozen at the edge of its existence. Light that grazes the shell slows, matter that approaches seems to linger, and the usual flow of cause and effect warps into an unfamiliar rhythm. The exotic shell, combined with the anti-gravity core and hollow interior, bends space-time so profoundly that the very experience of time becomes relative. What passes in seconds for a distant observer could stretch into eons for an object near the boundary. This effect is a consequence of extreme gravitational time dilation, magnified by the Gravastar's unique structure. Unlike black holes, whose singularities create points where classical physics breaks down, Gravastars maintain a smooth, continuous boundary. The shell itself becomes a liminal zone, a frontier where time slows to a crawl, and the ordinary rules of motion, energy, and causality are stretched almost to the breaking point. Matter that touches this surface does not vanish. It is trapped in a slow-motion dance along the shell, orbiting, smearing, and interacting with extreme precision, while the core remains pristine and untouched. The implications are staggering for observation. Photons emitted near the shell are redshifted to near invisibility, appearing almost frozen in time as they escape into the universe. Gravitational waves generated by infalling matter or nearby cosmic events arrive delayed and stretched, carrying the imprint of the shell's temporal distortion. To astronomers, these signals are subtle, faint, and tantalizingly enigmatic, like glimpsing a world suspended on the edge of reality, a place where the universe holds its breath and observes without interference. This surface that defies time is also a philosophical paradox. The Gravastar embodies a threshold between existence and inaccessibility. Objects can interact with the shell, yet nothing reaches the interior. Events can occur, yet they unfold in stretches that challenge human perception. It is a reminder that the cosmos operates on scales and principles far beyond intuition. The boundary of the Gravastar is simultaneously approachable and unreachable, a zone where physics stretches to accommodate extremes without breaking, and where the ordinary flow of life and death, cause and effect, is subtly suspended. Conceptually, the shell becomes a kind of cosmic mirror, not reflecting light, as some Gravastar theories suggest, but reflecting the very flow of time. Moments linger, processes stretch, and the universe seems to hesitate at the edge of this extraordinary object. In this way, the Gravastar's shell is not merely a physical boundary but a temporal one, a place where the rules of chronology bend, creating an interface between the tangible universe and the hollow, eternal interior. Ultimately, a surface that defies time is one of the Gravastar's most profound mysteries. It is a frontier where physics, perception, and cosmic scale converge, producing a liminal zone that is almost as alien as the hollow core itself. Here, at the edge of impossibility, the universe demonstrates that time can be stretched, slowed, and reshaped, and that the Gravastar exists not only as a structure in space, but as a monument to the malleable nature of time itself. Eternity is embedded in a shell, and the real becomes the unreachable. If countless Gravastars roam the galaxy, their mass could account for the invisible weight holding galaxies together. Dark matter has long been one of the universe's deepest mysteries. It exerts gravitational pull, shapes galaxies, and influences cosmic structure, but it does not emit, absorb, or reflect light. Gravastars, with their hollow interiors, exotic shells, and near invisibility, are tantalizing candidates for this unseen matter. Their presence could explain the missing mass without requiring a wholly unknown particle or exotic field. They are extreme objects that behave in ways consistent with the gravitational fingerprints of dark matter. Unlike ordinary stars, Gravastars are quiet, almost undetectable. They do not blaze with radiation, they do not produce jets, and they interact with light only subtly, via gravitational lensing or faint reflections. Yet their mass is real, concentrated in their shells, and spread across the cosmos in ways that could generate the gravitational scaffolding necessary to hold galaxies together. Clusters of Gravastars could create invisible webs of influence, subtly steering the motion of stars, gas, and dust, providing the structural backbone of the universe without ever being seen directly. The possibility also explains some persistent anomalies in astrophysics. Observations show stars orbiting unseen mass, and galaxies moving as though tethered by invisible hands. Traditional dark matter models rely on particles that have never been directly detected, creating tension between theory and experiment. Gravastars, by contrast, are extreme but physically plausible objects. Their effects on surrounding matter, orbital deviations, gravitational waves, lensing signatures, match many of the observations attributed to dark matter. In this sense, the universe could be populated not with hypothetical particles, but with tangible, albeit invisible, gravastar remnants. Yet the idea raises further questions. How many gravastars would be required to account for the total mass of dark matter? How did they form in sufficient numbers? And why have we not detected more subtle signatures of their presence? Here, theory and observation meet the edge of possibility. Gravastars could populate the galactic halo, hidden in darkness, only betraying themselves through the faintest gravitational effects or rare interactions with ordinary matter. Each one is small on a cosmic scale, yet collectively, they could weigh heavily enough to shape the universe. Philosophically, this hypothesis transforms the way we imagine cosmic structure. What we perceive as invisible may not be abstract or exotic in the particle sense. It may be a population of real, extreme objects, each a hollow, eternal gravastar, quietly maintaining the universe's balance. Galaxies, clusters, and filaments are not held together by unseen forces alone, but by ancient, silent objects that defy destruction, persist indefinitely, and govern motion through pure gravitational influence. Ultimately, the idea that gravastars could be dark matter is both elegant and humbling. The same objects that imitate black holes, that defy time, and that whisper with faint tremors, could also account for the missing mass of the cosmos. The universe may be filled with hollow, silent sentinels, invisible yet essential, holding galaxies together with the quiet power of gravity. In their shadows, we find not only the missing matter, but a reminder that the cosmos operates with layers of subtlety and hidden complexity far beyond human perception. Some speculate that the interior vacuum could connect to other regions of space-time, or even other universes entirely. The hollow core of a gravastar is not merely empty, it is a space dominated by vacuum energy, a medium so extreme that it resists collapse and shapes the shell above it. Some theorists propose that this unique interior could serve as a bridge, a corridor through the fabric of reality itself, linking distant points in our universe, or even forming gateways to alternate universes within a broader multiverse. In this vision, gravastars are not just endpoints of stellar evolution, they are nodes in a cosmic network, portals hidden in plain sight. The physics behind this speculation is subtle but profound. The enormous outward pressure of vacuum energy, combined with the shell's exotic matter, creates conditions where space-time may bend and twist in ways forbidden in ordinary stars. If these distortions extend beyond conventional four-dimensional space-time, the interior could form a stable conduit through higher dimensions. Particles, radiation, or even entire fields of energy could, in principle, move along these channels, leaving the gravastar in one region of space and emerging somewhere else entirely. The possibility transforms our understanding of these objects from isolated anomalies into potential cosmic crossroads. Observationally, detecting such a connection is extraordinarily difficult. Any interaction between universes or distant regions of space-time would be subtle, encoded in tiny perturbations of gravity, strange patterns in high-energy particles, or unexpected anomalies in gravitational wave signals. We might detect evidence indirectly, echoes that arrive too early or late to match expected collisions, matter appearing to vanish or reappear, or gravitational lensing that cannot be fully explained by visible mass. Each subtle clue would hint at a reality larger and stranger than our current models, one in which gravastars are gateways as well as extreme stellar remnants. The philosophical implications are equally staggering. A gravastar could embody the idea that what appears empty and inert is, in fact, a conduit to something beyond comprehension. Its hollow core, a region devoid of ordinary matter, yet brimming with energy, might connect not only to other locations within our universe, but to entirely separate realms of existence. The universe, in this sense, contains hidden passages, and gravastars could be the natural bridges. Stable because they are balanced between gravity, vacuum energy, and the extraordinary properties of exotic matter. This concept also reframes our understanding of cosmic isolation. Stars, galaxies, and black holes are traditionally seen as bounded entities, confined to their local regions of space and time. Gravastars, by contrast, suggest that the extremes of physics might produce objects capable of transcending these limits. They could, in principle, link far-flung parts of the cosmos, or even connect universes in ways that challenge our notions of locality, causality, and the finality of space. Ultimately, the multiverse connection paints gravastars as more than stellar remnants. They become potential gateways, cosmic junctions where the fabric of reality itself stretches and folds. The hollow core, once imagined as nothing, may be a corridor to the unimaginable, hinting at a universe, or multiverse, where boundaries are porous, and the extremes of physics create not only structure and stability, but pathways to realms beyond our perception. In the heart of emptiness, there may lie the ultimate bridge, a whisper of infinity connecting all that exists. If both exist, their collisions would produce signals unlike anything we've seen. Half echo, half collapse. A black hole is a cosmic devourer, swallowing everything that crosses its event horizon, while a gravastar is a master of restraint, reflecting, preserving, and subtly interacting with its surroundings. When these two extreme objects converge, the encounter would be a clash of fundamentally different physics, producing gravitational waves and electromagnetic signatures that challenge our most advanced models. The dynamics of such a collision are extraordinary. As a black hole approaches a gravastar, its immense gravity would pull at the shell, compressing it and generating intense vibrations. The hollow interior, however, resists collapse, pushing back with vacuum energy and preventing the formation of a singularity. Matter and energy that might normally be swallowed are instead trapped in oscillations, bouncing off the shell in echoes that combine with the tidal forces of the black hole. The resulting gravitational wave pattern would be unlike anything observed from binary black hole mergers, a complex symphony of peaks, delays, and repeated signals, partially absorbed, partially reflected, partially stretched by extreme time dilation near the gravastar's shell. Light behaves in equally bizarre ways during such an encounter. Photons skimming the gravastar's shell could be deflected, delayed, or trapped in temporary orbits, while the black hole's gravity warps their paths further. To a distant observer, this could create a shadow that flickers, shifts, and oscillates, an ever-changing silhouette of interacting extreme physics. The gravastar would appear to dance around the black hole, its shell ringing and vibrating like a colossal drum, while space-time itself stretches and bends to accommodate forces that are simultaneously opposing and cooperative. The collision would also be a laboratory for the limits of physics. Quantum effects at the gravastar's shell would interact with the black hole's singularity-driven curvature, possibly producing phenomena never before considered: unusual particle emissions, faint high-energy bursts, or unexpected distortions in nearby fields of matter. Each effect would be encoded in gravitational waves and light, offering astronomers the opportunity to probe the interface between classical relativity, quantum mechanics, and exotic matter. The universe, in essence, would be conducting an experiment on the boundaries of the possible. Philosophically, the meeting of a gravastar and a black hole is a confrontation of extremes: consumption versus preservation, silence versus collapse, emptiness versus singularity. It is a collision that embodies the duality of the cosmos itself, where some structures annihilate and others endure, where one object erases and another preserves, and where space-time itself becomes a canvas for forces beyond human intuition. Ultimately, If such an event were observed, it would redefine what we understand about massive objects, the life cycle of stars, and the nature of gravity. It would demonstrate that the universe is capable of producing interactions not only extreme in energy, but complex in subtlety, where echoes and collapse coexist, and where the quiet, hollow Gravastar asserts its presence even in the face of a devouring singularity. In the meeting of these two cosmic titans, we would glimpse the full spectrum of the extraordinary, a spectacle of physics that is as beautiful as it is unfathomable. Future telescopes may peer closer to event horizon edges, searching for the faint shimmering of a real surface. Unlike black holes, which are defined by an invisible event horizon beyond which nothing escapes, gravastars have a tangible shell, thin, ultra-dense, and nearly invisible, but real nonetheless. Observing it requires instruments of extraordinary precision, capable of teasing out the tiniest anomalies in light, radiation, and gravitational signals. Every photon that grazes the shell carries encoded information, a faint shimmer hinting at a surface where classical black holes would have only emptiness. High-resolution imaging techniques, such as those employed by the Event Horizon Telescope, are being refined to detect these subtle cues. Light bent around a gravastar's shell does not vanish. It circulates, lingers, and can escape at slightly altered angles, producing patterns that differ subtly from those of a black hole's shadow. Future arrays of telescopes, linked across continents and even in orbit, aim to capture these minuscule distortions, seeking evidence of a real boundary hiding in plain sight. Every slight deviation, every faint oscillation in light intensity or position could point toward a gravatar. Gravitational wave observatories, too, will play a crucial role. Collisions involving gravastars produce echoes, vibrations, and delayed signals, all of which encode the shell's properties and the hollow interior's energy. As detectors become more sensitive, astronomers will search for these faint reverberations, sifting through the noise of the cosmos for the telltale signature of a real surface. Unlike the clean absorption of a black hole, the gravastar's shell leaves a subtle imprint, a fingerprint that, once recognized, could transform our understanding of extreme astrophysical objects. The pursuit of the undetectable also pushes theoretical models to new extremes. Simulations must account for exotic matter, anti-gravity cores, vacuum energy, and time dilation effects near the shell. Each scenario generates unique observational predictions, guiding telescope design and observational strategy. Researchers are essentially trying to photograph and measure something almost entirely hidden, a surface that bends light, warps time, and whispers through gravitational waves, all while remaining nearly invisible. Philosophically, detecting the undetectable is a testament to human ingenuity and patience. The gravastar challenges our intuition about what is real and what can be observed. It demonstrates that the universe may conceal its most extreme structures, not by absence, but by subtlety. Observing a gravastar is not merely a technical feat, it is a test of perception, requiring us to read the universe in its quietest, most refined language, where echoes, shimmers, and vibrations tell the story that light alone cannot. Ultimately, the quest to detect gravastars is about confronting the limits of knowledge. Each photon, each gravitational wave, and each micro-distortion of starlight is a potential clue. By peering closer to the edges of what we once thought were event horizons, astronomers hope to reveal surfaces where none were expected, to find reality in the shadows, and to illuminate objects that exist on the boundary between the observable and the almost impossible. The undetectable may yet become visible, and with it, the universe may show us a new layer of its most extraordinary and enigmatic creations. Gravastars revive an ancient idea: stars made not of matter, but of dark energy, glowing in silence. Unlike conventional stars, which burn through nuclear fuel and radiate light, gravastars are powered by something far stranger: the vacuum energy of their hollow interiors. This energy does not flare, combust, or ignite. It simply exists, pushing outward against the ultra-dense shell, stabilizing a structure that defies collapse and defies expectation. In this sense, the Gravastar is a star reborn, a cosmic object that shines not with fire, but with the quiet, persistent force that underlies the universe itself. The concept is revolutionary. While ordinary stars age, burn out, and die, Gravastars persist. Their hollow cores filled with dark energy prevent a singularity from forming, and their shells of exotic matter maintain integrity under pressures that would crush ordinary material. They are eternal in a way that ordinary stars cannot be. Glowing faintly, not with light, but with the subtle curvature of space-time, the gentle radiation of vacuum energy, and the faint interactions of the shell with passing matter and light. A Gravastar's glow is the universe's whisper, a silent radiance detectable only through its gravitational influence, minute thermal emissions, or the faint echoes of waves bouncing off its shell. This resurrection of the dark star idea connects modern physics with the dreams of early cosmologists. For decades, theorists speculated about the possibility of stars powered by something other than nuclear fusion, hypothesizing objects made of exotic energy that might evade direct detection yet influence cosmic structure. Gravastars fulfill that vision. They are massive, structured, and stable, yet almost entirely hidden from conventional observation. They demonstrate that the universe can create objects in which mass and energy exist in extreme balance, where gravity is countered by vacuum energy, and matter, if present, only decorates the shell rather than defining the interior. Observationally, these silent stars leave subtle footprints. They influence the motion of nearby bodies, bend light in precise ways, and generate gravitational wave signatures that differ from traditional stellar remnants. Over cosmic time, populations of Gravastars could affect galaxy dynamics, serve as seeds for structure, or even contribute to the invisible scaffolding we attribute to dark matter. Unlike luminous stars, their presence is inferred indirectly, yet the patterns they leave across space and time are unmistakable for those attuned to their quiet signals. Philosophically, the dark star reborn challenges our notions of light, energy, and existence. It embodies the principle that power need not be loud, that influence need not be visible, and that the universe can harbor structures that thrive in silence, sustained by forces beyond ordinary perception. Gravastars illuminate the cosmos not with fire, but with the profound subtlety of vacuum energy, demonstrating that the most extraordinary objects may radiate quietly, shaping reality without spectacle. Ultimately, the Gravastar is a rebirth of cosmic imagination, a dark star that glows in silence, eternal and enigmatic, a monument to the universe's ability to create structure from emptiness, stability from extremes, and radiance from the quiet energy that pervades all of space-time. In them, the universe shows us that even in darkness, there is enduring light, subtle, silent, and eternal. Just when we think we've mapped reality, something even stranger emerges, forcing us to rewrite the edges of our understanding. Gravastars are a perfect example of this cosmic audacity. For decades, black holes were considered the ultimate expression of gravity and stellar death, points of infinite density where physics itself seemed to end. Then theorists proposed Gravastars, objects that imitate black holes yet evade their defining extremities. Suddenly, the universe was not only stranger than we imagined, it was more subtle, more intricate, and far less obedient to our expectations. This unpredictability is a hallmark of the cosmos. As observational technology improves, we continue to discover phenomena that challenge classical models. Gravitational wave echoes that hint at hollow interiors, photon rings that shimmer differently than predicted, and objects whose mass behaves like dark matter without ever revealing a traditional surface. Each anomaly is a reminder that our understanding is provisional, that the universe writes its own rules, and that what seems impossible today may become the foundation of tomorrow's physics. Gravastars, silent yet massive, hollow yet influential, exemplify this principle. They force scientists to reconcile the extremes of relativity with the subtleties of quantum mechanics, offering insights into phenomena previously relegated to thought experiments. the implications extend beyond gravastars themselves. If these objects exist, they could reshape entire fields of astrophysics, altering our models of stellar evolution, affecting the dynamics of galaxies, and even suggesting new pathways for understanding dark matter and vacuum energy. Every discovery like this acts as a lens, refracting our knowledge in unexpected ways and revealing layers of the universe previously invisible. It is as though reality is a living manuscript, continuously edited by forces we are only beginning to perceive, with gravastars as some of the most elegant footnotes in the story. Philosophically, the universe that never stops surprising us challenges our sense of certainty. It reminds us that exploration is endless, that the cosmos is not a static puzzle, but a dynamic, evolving canvas. Each theoretical leap, each faint signal captured by telescopes and gravitational wave detectors, stretches the imagination while testing the limits of observation. Gravastars are a metaphor for this principle. Hollow, nearly undetectable, yet rich in consequences. A silent testimony to the fact that the universe can harbor secrets in forms both beautiful and elusive. Ultimately, the ongoing surprises of the cosmos underscore the humility and wonder inherent in scientific discovery. Every observation, every anomaly, every faint whisper of light or gravity invites us to rethink assumptions and embrace the unknown. Gravastars, if confirmed, are not just extreme objects. They are symbols of the universe's relentless creativity, a reminder that even in the void, there is structure, meaning, and the capacity to astonish. In the quiet echoes, the faint shimmers, and the unexpected patterns, the cosmos continues to teach us that no matter how much we know, there is always more, always something beyond the horizon, waiting to redefine what we believe is possible. If these objects exist, they are neither dead stars nor cosmic traps. They are new forms of existence, waiting quietly at the edge of what we can imagine. Unlike black holes, which consume, annihilate, and leave nothing behind, gravastars defy destruction. They are hollow yet massive, silent yet influential. Simple in appearance but unimaginably complex in structure, their shells of exotic matter and cores of vacuum energy create entities that are stable, persistent, and fundamentally different from anything we have previously classified. If black holes are the monsters of the cosmos, then gravastars are the hidden predators, subtle, unassuming, yet capable of bending the universe in ways we are only beginning to perceive. The monstrous nature of gravastars lies not in violence, but in their quiet defiance of expectation. A gravastar does not roar, it whispers through gravitational waves, faint photon echoes, and subtle orbital effects. Yet these whispers carry the weight of immense mass, capable of influencing stars, bending light, and shaping galactic structures. Matter that approaches does not vanish into a singularity but is smeared across the shell, interacting in ways that preserve energy and information. They are predators of a different kind, not destructive but absolute in their persistence, quietly asserting influence across vast distances without drama or spectacle. If gravastars are widespread, their presence could rewrite our understanding of the cosmos. The invisible scaffolding attributed to dark matter could in part be a population of these extreme objects, each one exerting influence without revealing itself through traditional observation. Galaxies, star clusters, and even cosmic filaments may owe their motions and stability to these silent titans. Unlike black holes, which consume and conceal, gravastars maintain a balance that is paradoxically violent in its subtlety. They resist collapse, endure time, and leave only faint, nearly imperceptible signatures in the fabric of space-time. Philosophically, gravastars challenge the limits of imagination. They remind us that the universe's most extreme creations need not conform to our notions of destruction or spectacle. Power can manifest in silence, influence can exist without visibility, and existence itself can take forms beyond our previous comprehension. Gravastars are monstrous not because they annihilate, but because they persist, defy our expectations, and exist at the edge of the observable, quietly shaping reality while remaining almost entirely hidden. Ultimately, If gravastars are real, they are a testament to the universe's ingenuity. They are proof that creation does not always obey intuition, that stability can emerge in extremes, and that the cosmos has hidden mechanisms operating silently at the boundaries of physics. They are monsters not in fearsome display, but in the quiet certainty of their presence, eternal and unyielding, waiting at the edge of what we can imagine. In these hollow, vibrating, silent shells, the universe may have produced its most enigmatic and enduring objects, monsters that do not roar, yet command everything around them. And now, as our journey through the dark heart of the universe comes to an end, let your thoughts drift like stardust through the quiet. We have wandered past dying suns, through shadows masquerading as black holes, and into the ghostly interiors of gravastars, those hollow, shimmering echoes of collapsed stars that rewrite what it means for a universe to be strange. We've learned of shells thinner than imagination, cores filled with silent oceans of dark energy, and boundaries where time itself stretches and softens, like the surface of a cosmic drum. We've seen how light can orbit forever without escape, how gravity can hold back a star's collapse without tearing reality apart, and how the universe is still full of secrets, waiting quietly in the dark. But in all of this immensity, remember something gentle and grounding. You are here, a conscious observer in a universe that is vast, ancient, and beautiful, and somehow, through a tapestry of impossible coincidences, you get to witness it. So let your mind rest. Let gratitude settle softly on you, like starlight falling across a calm sea. You are part of this great cosmic story, woven from the same particles that build galaxies, that glow inside stars, that drift through nebulae 1,000 light years wide. Tonight, let the universe feel simple again. Let the quiet cradle you. Let sleep arrive like a gentle tide, carrying you into its own peaceful gravity. Thank you for joining this journey among the stars. Until next time, rest well, dream deeply, and drift easily into the night.